Thank you. Raymond, maybe I start, and I have the coffee later. I will have the coffee later. Yeah, or you can bring it here. I will drink it during my presentation, no problem. So, the two lectures I'm going to give today are about some stuff more practical, okay? Because it's cool to have all this notion about the age of the Earth, the isotopes, the mathematics, the error, blah, blah, blah. But, you know, all these numbers, you have to acquire them. And to acquire them, you need a lab to be able to retrieve some good numbers. And so I'm going to present you first the clean lab processing. So how we go from the sample that we collect on the field up to some chemical compound we are able to measure with a mass spectrometer. So let's start with some basic notion of rock sampling, selection, and preparation before the clean lab. So I don't know if you remember the first day I told you about the way the geochemists are sampling on the field. Okay, mainly we love to have several samples of a single outcrop, especially a single lithology, to be able to check if our isotopic composition is homogeneous in a single rock family. For example, if you have a gabbroic outcrop, it's better to have 4 or 5 samples so that we can measure 4 or 5 times the numbers. Then we check about the heterogeneity of the outcrop. But not only the way we are sampling the rock on the field, it's slightly different than the way people were sampling in the past to do, for example, geological mapping. We need, for example, a large piece of sample if you need to date. If you need to date and to get zircon from your granite, for example, you need a big piece like this, okay? And of course, if you deal with magmatic system, magmatic process, you don't want to have secondary effect due to the surface alteration. So sometimes when you are working in tropical country or a country where you have a heavy, dense cover of, of trees, the surface of your outcrop is not that good for sampling for magmatic system. So you need to dig and to retrieve some fresh sample. So now, because we are in a modern time, everybody have a GPS, but also the positioning of your sample is very important. And so this is why you need to have your book, you know, your field book, and your observation you do, take a picture, you label correctly your sample, and you try to get a sample which is devoid of alteration, okay? Especially for magmatic. If you deal with alteration process, then you prefer to have the surface. And then you come back to the lab, and you you have an idea in mind. You want to solve a problem, okay? This is a geological problem you want to solve. I don't know, an ophiolite, the origin of the ophiolite, a magmatic differentiation theory. You want to check the magmatic differentiation, whatever, and you went on the field to sample with this idea in mind. But you need to also get some sample that you can crush and which are reliable to the problem where we will answer the problem you want to answer. For example, I don't have the pointer of Michel, but here, typically, I'm working a lot with my PhD student in Oman sample, okay, like peridotite, dunite, etc. And he did a PhD on this. He just defended on the mantle transition zone, the dunite, okay, the more petrological mantle transition zone. This is what kind of sample we can have on the field. If you sample this kind of rock, you see it's totally heterogeneous. Here you have only olivine. Here you have olivine with diffuse plagioclase inside. If you collect a sample, which is in the middle of this here, then in terms of geochemistry and wall rock geochemistry, you will not be able to interpret anything about the signature you are going to have from this rock, because it's heterogeneous. It's deeply heterogeneous in terms of mineralogy. So that's something also important. When you come back to the lab with your sample, you have to crush your sample. For geochemistry, principally, we do either we crush it to make a powder to make the wall rock analysis, or we crush it to separate the mineral, or we crush it to separate some mineral to date. Of course, we do thin section after that, etc. This is the basic what you do in the lab. When you crush a sample, if I crush a sample which is a mixture between this one and this one, I'm not sure about what kind of interpretation I can do with the signal, not only the isotopes, but also the trace element, major element. Okay? So, before going into the geochemical lab, the thing important I would like to say is you need to be sure that your sample and your powder, after it's crushed, is totally representative to the rock you want to measure. Okay? Imagine you have a pegmatite with crystals that big. So normally we don't do wall rock with pegmatite, but this time you really want to know the pegmatite. Oh yes, thank you. You really want to know. Huh? No. Just the light. No. Which button is it? Ah, thank you. Huh? Yeah, but my computer will, Macintosh will start to, I want to install, blah, blah. I don't need it. I will. So, I was like in a pegmatite. If you really want to have, if you have crystals that size in your rocks and you want the whole rock composition of your pegmatite, then you need to crush this so that you're sure that the composition of your rock is homogeneous and representative of your rock. If you have a basaltic glass that you have sampled deep in the oceanic ridges, you need this glass is homogeneous. You can work, I have worked with glass chips which were like 3 millimeter on 2 millimeter, like 100 milligram of glassy chips. They are representative of the rock. Okay? So that's something very important. When you go into the crushing facility, this is the crushing facility we have in Toulouse. You have different type of crusher. This is a jaw crusher, the basic one, crush like this. This is a agate mortar. If you have some crusher specific for mineral separation, you have a pulverizette like the one you have here in Pune. Okay, but before crushing your rock, be sure that you are crushing something that you will be that you can use after. Okay, when you are going to interpret your sample, because if you miss this step, the months you are going to spend in a clean lab to do your measurement, and the weeks and the night you are going to spend in front of your mass spectrometer to measure the isotopic composition are no use. If you miss the crushing, if you miss the sample separation, there is no use to go into the clean lab. And trust me, it happened, even to me. Okay? Sometimes I realize that I did not crush correctly my sample. I have, for example, cross-contamination in the mortar. I realized that my measurements were not correct. And you go back to the lab. No problem in the clean lab. No problem in the mass spectrometer. No, okay. No problem in the clean lab. Oh shit. And then go back to the crushing, and you realize that somebody the day before you have crushed, for example, cyanide in the same aggregate mortar, and you came with your peridotite. And it's bizarre, you find the cyanide isotopic composition in your powder. Okay, you laugh, but when you have worked months to get your numbers, then, okay, so it's very important. If one day we collaborate, I hope you will become a very famous scientist. You do a PhD, for example, in collaboration between India and France, and you collaborate with me in my lab, you go to my lab, I will be very careful on the way you have crushed your sample, you have prepared your powder, because we will not spend like months in the lab doing measurements if your numbers are not correct at the end. So that's the crushing part. For just a little example of a specific stuff that you can do also else than doing wall rock analysis is mineral separation. So when you want to do mineral separation, you don't make a powder from your rock, you make a sand, and you want to separate specific minerals. So either it's for isochrone dating, like we see some days ago, okay, you separate pyroxene, plagioclase, etc., etc., and you keep also the wall rock, or if for zircon dating. This is another process. Zircon dating, typically, you want to separate some mineral which are of very little abundance inside your rocks, and so you are not going to make a sand and manually try to find the zircon lost in a big sand of different minerals. You need some techniques to get your zircon. Typically, the techniques is shaking table like this. So you put your sand here. The table is shaking is water. In fact, gravity is separating the heavy mineral from the light mineral. You are doing what the rivers and the sea is doing in a natural condition, but in a quick way in your lab. You have some magnetic separator. So you put your powder inside here. It goes through a big magnet with a very intense magnetic field that you can tune, and then you can separate your minerals in terms of their magnetic affinity. Okay. And at the end, the last step, no, not the last, you have dense liquor separation. Dense liquor separation, if you buy some very, very, very dangerous and nasty products, which are this liquor, very dense, they have a density which is close to the density of your mineral. So you pour, after doing all that, the magnetic and friends, etc., you pour your powder inside the liquor. The mineral which are lighter will fall. The mineral which are heavier will fall on the bottom. The light minerals will stay in the surface of your dense liquor. And you use different liquor with different density to get rid about the minerals to select or to get rid the minerals you want or you don't want. Okay. So there are some many liquors that are completely forbidden in chemical lab because it's so we use typically methylene iodure now and bromo something, but we only use two because the other are forbidden to use in the lab. Okay, that's for mineral separation. And this is not something I'm going to tell you today because I'm going to tell you about isotopes, and this is a specific case of dating, but I'm going to tell you what we do with wall rock powder or mineral separate, but for an isotopic tracing purpose. So, we work in what we call a clean lab. Okay, so there are many names for this kind of clean lab. ISO something clean lab, class 10,000 clean lab, etc., etc. In fact, there is no specific name because these labs were home design, and they are still home design. For a geochemical clean lab, there is not really companies who are devoted, who can give you and build to you a clean lab exactly like the same you have in another lab. Because normally you buy you build a clean lab for 20 or 25 years, and so this company, they did not survive. They waiting that somebody is building a geochemical clean lab. So this is something which is home design, and there is no clean lab like the other. I mean, if you go to different city in France, you have different clean lab. The philosophy is different. They are not made the same, but there are some logic in the way they are built. So clean lab, the cost of a clean lab, because I can tell you because I have built one and I'm in the process of building a second one. The cost of the clean lab is 1,400,000 euro, or in dollars is $1,600,000. So it's very expensive, very, very expensive. And so it's very strange because you say, I'm a geologist, I'm go on the field, I'm collecting this kind of dusty, altered rock, you know, in a condition where you have alteration, animals, you know, on the top, etc., grass, and then we need a 1 million lab to retrieve the elements. And in fact, the reason is the elements you are going to measure in your rock, maybe they are of little abundance in your rock, but that can be very easily contaminated. Very easily contaminated. And especially during the process of separating them. Because the product, the compound, and everything you are going to use to extract this element from your powder, from your minerals, can trap very easily and dissolve very easily the element you are interested with, and then you can contaminate your sample. This is why you need a very clean environment, even if your rock doesn't look that clean when it's arriving inside your laboratory. So typically, this is the lab the way it was designed in Toulouse. We are going to extend it, I mean, double, but the philosophy of a clean lab is basically overpressure. Totally the opposite to, for example, a biological clean lab. A biological clean lab, you don't want the germ to escape your lab. In geology, you don't want the germ to enter the lab. Yes, and so it's overpressure. Means that you don't want to enter with dust, and everything from the outside should not enter into the lab. So typically, everything here, all this surface is Michel, comment tu dis étanche en anglais? Waterproof? No. Airproof? I'm looking for the term in English to say it's completely isolated in terms of air flux. Okay, I don't remember the term in English. But the only way the air can come out from my lab is from the extraction of the air I design and I put inside the lab. So I control the air flux in the lab. So there are some very big machines who are fluxing the air, filtering, temperature control, water content, hygrometry control, fluxing the air inside my lab with the specificity I design. And there are some apparatus inside the lab who are sucking out the air and cleaning it and put it in the atmosphere. So there is no other way that the air can enter except when I want to enter inside the lab and I have a SAS here. Okay, so I enter here. I remove my shoes. I enter here. I put some clothes. I change my clothes. I put protection. And there is a secondary door here, and in fact you have a gradient of pressure. This is a normal pressure, overpressure, and overpressure. And in fact, when I'm traveling inside the lab, the cleanest part is the part which is the far from the entrance. So that's the very fancy isotopes, very easy to contaminate room here, we call the isotopic room. It's overpressure to this room, which is a normal room for working, which is in overpressure to the south, overpressure to outside. Okay, and here this is where all the other people are working. In a clean lab, everything is on. There is no metal and no glass. Why? No metal, we can understand because it can be rusted by the atmosphere because we are using acid. But why no glass? Because what you are dissolving is silicates. So you are using products which can dissolve silicate. And a glassware is made of silica. So if you have glassware in a clean lab, gently they will be dissolved. Normally they don't, but because we are leaking some acid vapor, they will be dissolved. So no glass in a clean lab, and of course no metal, especially if you are doing lead. Okay, isotopes, you don't want any metal. So it's full cover with plastic. This is in plastic. This is in plastic. Okay, the bench are in plastic. Everything is in plastic. Or you can cover with plastic or with some plastic paint if you don't have. And sometimes you don't have the money to buy everything in plastic because it's very expensive. So sometimes you have a normal one from lab, and we are covering it with some plastic painting specific. So I have my sample. I have crushed them in my crushing facility, and you are going to measure them. You have 20 samples in some clean pots. You know, not like you are. It's a clean lab. You are not going to enter in a clean lab with large jars of 2 kilograms of powder, okay? Because it's dust-free, so powder is a dust. And then you are arriving in the clean lab, and the first things, when you want to measure either major element, trace elements, or isotopes, you need to take a fraction of your powder to process into chemistry. So to collect a fraction, you need to know exactly what kind of fraction. So I'm going to take an example with wall rock. Okay, we forget about minerals. I want to measure the trace elements and the isotopes in my wall rock sample. This is normally what I'm doing when I'm working in a clean lab. So there is a specific place in the lab here. The weighing unit, where you have the weighing area. This is an isolated part of the lab with two precision weighing unit like this, which can measure up to, so this is gram, up to 10 of milligram, even lower than that. And you are going to weigh the quantity of powder you want to measure. Typically, you are weighing between, for a rock, I'm working for magnetic problem, between 30 milligram and 250 milligram of powder. Not less, not more. Not less because you can have some problem of heterogeneity in your powder, and then you are not sure you are measuring really the composition of the rock if you are measuring too small amount. Not more because it's a very long process to dissolve. You have to remind that your rock is maybe 1 billion year, and the nature did not succeed to dissolve it in 1 billion year, and you need to dissolve it in 1 week. So you must have a very fine powder, and you need to have very aggressive reactive, and you need time. Okay. So of course we can go faster than the nature, but still it's a long process. And you need to weigh this sample. It's in some beakers which can resist the acid and the temperature you are going to use, of course. Typically it's Teflon. Teflon is perfect. Okay, there is Teflon beakers, and all the labs in the world are using Teflon beakers coming from a single company in the US called Savilex. I have no money interest in Savilex, but everybody is using Savilex. So, and what is a typical round in geochemistry? You come with your 25 sample, not 200, okay? Otherwise you will spend days, because weighing precisely 20 sample, it's 3-4 hours work. And you are not only weighing your sample. You are weighing also standard rock, standard power, like the one you have, that you can buy, okay, from other laboratory or company, so that you will measure something which is known, and then you can check if your measure is reliable. And you are measuring, and this is very important, a blank, the noise, the pollution of your lab. And a blank is an empty beaker with nothing inside except some spike. I will explain after on the next slide for isotopes. Empty beaker which is going to follow the same procedure as if there was some powder inside. And this blank will be subtracted to your signal. Okay? Subtracted. For isotopes, it's a little bit slightly different. For blank, when you do ICP-MS, when you do major element, the blank is just a subtraction of what you are able to measure with your machine. Okay, you are measuring your sample. I have 3 ppm of, I don't know, lead, and my blank is 3 ppb of lead. Then my total lead is 3 ppm minus 3 ppb. But the problem is, for isotopes, the blank contribution is a contribution as the square of the concentration of the blank on the isotopic signal. So we must know the value of the blank even if it's very low, because it can change your isotopic result. So the only correct way to measure a blank in an isotopic study is to add a spike. Spike is an artificial so imagine this is the isotopic composition of your sample. Let's say it's rubidium. Okay, you have rubidium 85, rubidium 87, and you want to know precisely, really precisely, the concentration of rubidium. You can do it also for a sample. It works with a sample or with a blank. When you want to be precise, for example, in geochronology, all concentration are measured by spiking. You add an artificial solution called a spike, which has isotopic composition totally anomalous, isotopic composition that you never find in any sample on Earth. So you have your beaker, you have either your sample or your blank, and you add this spike. If you have no contamination during all your protocol, you are going to see the protocol, dissolution, separation, chemistry, blah, blah, blah. Then, at the end, you should find in a blank the same spike isotopic composition, because there is no contamination. You don't add any rubidium inside. You should find this. But if you are able to measure a little change in the isotopic composition, then the change in this isotopic composition will be due to the contamination. And here you have the result of a mixing between sample or blank with a normal isotopic composition and your spike. And if you are measuring this, then if you know your spike concentration, if you know your spike isotopic composition, and if you know the isotopic composition of your blank or your sample, for a blank it's a global isotopic composition of the continental crust, then you can come back to the concentration of your blank. And it's very precise. Okay? You can go down up to picogram, 10 to the minus 9 gram with this kind of precision. Okay? So this is around. You weigh 3 to 300 milligrams, 250, 300 grams. You are a blank, standard, and sometimes duplicates. It's nice also to have duplicates. And then you need to dissolve your sample. So dissolution is, there are many ways, many publications about the way you can dissolve samples. So I'm going to focus only on silicates, okay? Because I have some people dissolving trees, okay, in my lab, but I'm not going to focus on this kind of process. So what is basically dissolution? Dissolution is you switch to an earth scientist to a chemist. Chemists play with water solution, water-based solution. So you need to change your elements which are in a mineral into elements which are into solution, and then to play as a chemist. Okay, so for silicates, typically you need to destroy the silica tetrahedron, SiO2 tetrahedron, and the acid which is used to do that is the fluorhydric acid. It's a very dangerous one, okay, but it is very efficient. Okay, its property, fluorhydric acid. You have the formula here. Other way is to do what we call fluxing, but fluxing we are not doing it in a clean lab, and we are not measuring any isotopes when you do fluxing to dissolve. Okay. Of course, because we are chemists and we love to mix some product because it's fun, we are mixing HF with other reagents like nitric acid, chlorhydric acid, perchloric acid. So this one is specific. I will tell you at the end. And why? Because there are not only silicates in a rock, there are also oxide, okay, sulfur, etc. And HF is very efficient to dissolve the silicates, have no effect on oxide and sulfur-based mineral. So you need to use other type of reagent, and typically we use this one or mixed of these two in the same process. Of course, you need to have a very clean reagent because if your acid is more dirty, it has more, for example, neodymium than the neodymium you have in your peridotite, then you are going to measure the isotopic composition of your acid. So either you are rich and you can buy very expensive acid for the lab providers. So typically, when you are very rich, you buy half a liter of perchloric acid, and the price is 1,000 €. Okay. And sometimes I bought for very specific stuff when I was not able to purify myself. I bought 250 milliliters of fluorhydric acid at 1,500 €. So you are not using it like this, okay? But normally we purify them. We have a clean lab, okay? So we can purify them. So purifying is for nitric, chlorhydric, and even fluorhydric. Typical way to purify is to evaporate it gently, so that the dirty parts stay here. It's evaporate. We call it subboiling, and the clean part is collecting here, and this is the heating unit. Okay. Water. We have some water cleaning system. Typically, this kind of system here to deionize the water and purify it. We call it double distill, but in fact, it's not distilled. It's deionized. But you will see double distilled water in all publication, because before that it was distilled. Okay, and we still keep this kind of work. So the water supply in your lab is depend on the liter of water you need to use per day. Okay, if you need a lot, then you have a big water supply, and the bigger is it, the more expensive is it. Okay, and the different beaker, all the beaker you are using to deal with your sample, of course, are very clean, because you are recycling them and using them for one sample batch to the other. Normally, I keep some beakers specifically for example, depleted rock, and some beakers for enriched rock, so I don't have any memory effect, but you recycle them. I have beakers belonging to the beginning of my career, so 20 years ago. Yes, something like this. I still use them. And then you need to dissolve. So how to dissolve? That's basic chemistry. To dissolve a rock, that's chemistry, you need temperature, and you need pressure. Okay? If you want to increase the speed of your dissolution process, you need temperature and pressure. And also, because we are chemists, we love to shake also them a little bit, okay? So typically, in my lab, we are using 3 types of apparatus for dissolution. Microwave, okay, like a microwave you have in your room, okay? 2 types, This one is more for organic stuff. This one is for silicates. So you put your sample in sort of Teflon beakers specific, which are being specifically designed for microwave. You put them in the microwave. You program it. It's not a microwave like you have in the kitchen, okay? But you program it. There is a computer, depending on the protocol. You have the microwave. And most of the time, we only use hot plates. But temperature calibrated hot plates, which are sitting in this kind of boxes. Why they are sitting in this kind of boxes? I told you the clean lab is dust control. A normal geochemical clean lab is 10,000 per particle per meter square and per hour. So if you put a particle counter in my clean lab and you leave it for 1 hour, normally it should count not more than 10,000 particles per cubic meter per hour. But it's still dirty for isotopes. This is the general atmosphere of my clean lab, and in fact, when we are dealing with my beaker, and sometimes you want to evaporate, so the powder will be into contact with the external atmosphere. We are doing this in this kind of boxes, which have a specific filter on the top and exhaust air here. And in fact, the air, the 10,000 meter square particle atmosphere is sucking through this filter, is going fluxing on the top of my hot plate and my beaker, and then is exhausted there. And in this box, you have 100 particle per meter square per hour. Of course, we can think about having a total lab of 100 particle, but it's very, very, very expensive to reach this kind of level where in a room. So it's better to have some specific places where you can deal with this kind of dust atmosphere. So dissolving, there are several protocols. So I will not present all the protocols we can use. Typically, the base is HF, and then you mix with other compounds depending on your rocks. I will talk only about the protocol for mantle peridotite. So mantle peridotite, we use a protocol which is with perchloric acid, HClO4, and HF. Why? Because there is a lot of magnesium in the mantle rocks, and when you have a lot of magnesium and you don't use the perchloric acid, you can have some precipitation after dissolution of some fluoride compound, and this fluoride compound can trap your rare earth elements. Neodymium is a rare earth element, and so you have a solid stuff which is totally insoluble at the bottom of your beaker, and then you are losing your neodymium. So typically, for mantle rocks, we use a mixture between HClO4 and HF. Very aggressive. So you have to be very careful when you deal with this kind of stuff. And we are heating it at different steps. For dissolution, typically it's 100 degrees for overnight. Normally, in one night, you can dissolve it, your 1 milligram or 200 milligram of rock. And then we are evaporating the acid. And the property of the HF is taking out part of the silica during evaporation. So you are getting rid of a part of the matrix during the evaporation. And typically, with this protocol, we are evaporating at different steps. Here, they are written 100, 165, and 195. So you need to have a very good Teflon so that it can resist to this temperature. You need this step several times, and at the end, normally, you should have a salt, okay, of chlorure salt at the end, no silica anymore, and this salt should be can be dissolved in slightly acid water. Okay, it should be dissolved like this because you switch from a silicate to a normal salt that you can use in chemistry. And this is this salt that we are going to use to separate the element for isotopes. Or this is this salt that we are going to dilute directly to put in my ICP-MS to measure the trace element concentration. Okay? Because you have dissolved your rocks, then you can play as a chemist with it. So, to separate the elements in a clean lab, to separate like neodymium, to separate strontium, to separate lead, etc., you need to use ion exchange resin, water-based chromatography. Why we need to separate the element? Because typically the machine we have are not able to measure isotopic composition directly in a two solution when you have all the elements from the Mendeleev table. And second, this is a mass spectrometer. So I will explain this in my next talk. But typically, for strontium, you are measuring 87 strontium on 86 strontium. 87 is a mass. A mass spectrometer is measuring a mass. If you are not separating strontium from the other element, you may have 87 rubidium in your solution. The mass spectrometer doesn't care if it's rubidium or strontium. It's 87. And so when you measure your ratio, in fact, you are measuring the ratio of 87 strontium plus 87 rubidium on strontium 86. So we need some chemical protocol to separate the strontium. We call this purification. Okay? And so there are some industrial way, very, very good industrial way to separate this element from the other, but not very clean and very expensive. And fortunately, it exists some ion exchange resin. This is some stuff you can buy, which have the property to separate the element according to some specific protocol. And this is what this lady is doing in the laminar flow. So again, this laminar flow here, so we don't see that much, but laminar flow is a laminar flow with the air at with 100 particles per meter square per hour, because you are fluxing air on your sample, so you don't want to be very clean. And inside you have column like this. Oh, here this is a column made by the Biorad company, but you can home design your column. Inside the column you put some resin. Okay. This resin, you have many types of resin, and most of the time they are specific to what you want to do with it. You use a specific resin for neodymium, you use a specific resin for strontium, specific for lead, specific for lutetium, etc., for hafnium, blah, blah, blah. And the way you are playing to separate the resin, in fact, you are playing with the property of this resin, and globally, this is an exchange between, because you are in water-based solution, between the H+, the concentration of H+, the acidity, globally the pH of your media, and your element. The resin is trapping the element, and then if you add some H+, some acidic solution, then the H+ will replace the element in the resin according to their ionic radius. And then, playing with the concentration of the acid you are going to put in the resin, you can gently separate the element from the other. Okay, so you have a typical, like it's organic resin, DOX resin, and this one is a achrome specific resin also. So I will not enter into the detail of resin. We have different way to use them, but typically this is the profile of purification. Here you have the type of acid you are using. So here it's 1 mole HCl and 0.1 mole HF. 1.5 mole HCl, 2.5 molar HCl, etc., etc. So the normality or the molarity of the acid, when it's a big number, it's more acid, okay? And then here you have a profile. So when I put my sample inside, and then I use 1.5 molar HCl, and during, for example, from 5 to 15 milliliter, the rubidium will fall down from my resin but not the strontium. So I have a trash, put my trash, I put my 15 milliliter, I wait, I have a coffee, I come back, and then I reach this level, then I remove my trash, I put my specific beaker for strontium, put under my column, I continue to add 1.5 milliliter HCl, and between 15 and 30 milliliter, only the strontium is falling down. This is my purification protocol globally. There are many ways, okay, but this is one of the protocols. Then I continue because in my sample, I want also to retrieve other type of elements. I want also in my same sample to have, for example, the lutetium. I want to have the neodymium and maybe the lead. Lead is not exactly like this, but I want to have other, purify other elements. So I continue. I change the media. Then I get lutetium. Cool. Then I change the media and I get samarium plus neodymium. Okay? This one is ready for mass spectrometry. I just have to dry it. This one, I dry it and I will use it in another type of chemistry, other type of resin, in another type of column, the same day or the day after. And normally you have to dry it. And I use other type of acid, less concentrated. And again, I play with the volume, and at a moment, the neodymium will fall out, and the other rare earth elements will be away. So here you see there is a mixture of praseodymium and neodymium, but it's not a problem for mass spectrometry. This is typically the way we are extracting the different elements, not the isotopes, okay? We are extracting the elements. So I have the whole neodymium in this batch here. When I collect between 11 and 14 milliliter of this acid, I have the whole neodymium, and I suppose that the isotopes are not fractionated by the resin. This is true for this kind of element with a heavy mass. When you are dealing with the lithium isotopes, when you are dealing with calcium isotopes, iron, etc., stable system, they can be fractionated during this process. For example, you can have the lithium-6 going out of the column here, and lithium-7 going out of the column here. But this is not the case for strontium. This is not the case for neodymium. So that's the basic of what we call ion exchange chromatography applied to the isotopic chemistry. So you use, of course, very well purified acid, and you do this for the blank and sometimes also for the standard. Well, this is the ancient way with this kind of resin. Now, it was what I was doing during my PhD. Now, if you come to my lab and you want to do some isotopes, we are not going to use this kind of resin anymore because people have developed some specific resin which are really specific to one element. One resin for strontium, one resin for neodymium, one resin for lead, one resin for hafnium, etc., etc. And the property of this resin, in opposition to what you see, not this one, in opposition to this, if you make a mistake here, or here, I will take it because this one is still this. If you make a mistake here and you have not a big control of the normality, for example, you forget to control the normality of your acid, and you make a mistake because either putting 15, you put 20 or 25, then you are losing all your strontium. So people develop some resin, so that we call them specific. When you change the media, for example, you change from nitric to chlorhydric, or you change from concentrated chlorhydric to concentrated acid, then you change the behavior of the resin and the element will fall without any problem of volume. For example, I will show you with this one. So this is typically the protocol developed by Christian Pain in Clermont-Ferrand, who now are used in many labs in France. And typically, here you have a resin called SR spec. So first you are using only 200 milligram of resin instead of having very big column. Okay, so less resin, less probability of contamination. And second, in the strontium spec resin, when I'm still into acid media, like concentrated acid media, the strontium will never fall down, never. So, but all the other will fall down. So I can put my sample in a relatively concentrated nitric, like 2 normal nitric. Then I can play with concentrated acid to remove the other, clean, clean, clean. I put from, for example, I use 1 normal nitric, I use 7 normal nitric, and then I switch. So still all the elements are falling down, are going through the resin without being attached to the resin except strontium. And then when I change, I put water, or in this case slightly diluted nitric, and then the strontium will fall out. So it's very easy because I put concentrated acid, I can go for a coffee, I can go for lunch, still the strontium is still in my resin. Then when I come back, I just change the media, put water, strontium is falling out. Okay? And this is the principle of this chemistry which we are using. There are specific chemistry which are used for the different elements. This one is a specific chemistry for strontium and neodymium. I put my sample in the 2 columns which are stacked one on the other. This one is trapping strontium. This one is trapping rare earth elements. Then I unstack them. I put them in a separate place. Strontium here. Then I continue to put some acid until I consider that the strontium was purified. Then I add water. I get strontium. This one here, I take it. There are rare earth elements inside. I stack it above another column which is specific for neodymium, and then I do the neodymium chemistry on this column. The same day, on the same dissolution batch. So I do it in 2 days, although my wife complained, because normally if you do this, you start at 7 and you end at 9 at night. And so you can do it because it's a specific, this resin is specific, you can do it in 2 days. So the PhD students are doing it in 1 day, okay, except if they are married. I'm doing it in 2 days. So in 2 days, I have a stack of 12 columns. I book the wood to do it. So I have 12 columns, multiplied by 2, because you need 2 here. Multiplied by 3, sorry, if I'm doing in 1 day. I have 3 times 12 columns, so I can process 12 samples at once. Okay. So when I start with a Master 2 student or a PhD student, they don't do 12 at once, because if they make a mistake, they miss 12 samples at the same time. So we start with 2 or 3, and then if they succeed and they get good numbers, then we can go to 12. Okay. Sometimes when I'm very in a hurry, I can go up to 40 at the same time. So I book two benches, and I can process 40 samples at the same time because it's just a number of columns. And then it's a big job. So Christian Pin, this guy is Clermont-Ferrand, is a little bit crazy. He continued to develop this kind of specific chemistry, and then he applied it for all the isotopic systems you can use in magmatic geochemistry. And to be honest, I did not try to set up this kind of crazy stuff in my lab, because you have so many resin, so many acid, and you know all these resin are white. All the columns are the same shape. So you have to be sure that this one is for strontium, this one is for lutetium, no, neodymium, maybe lead. No, and then you make big mistakes. So I don't know how we have a very, very good engineer to help him, I know, in Clermont-Ferrand. Huh? Sorry?
You're not receiving your cell calls while you're doing this.
No, and mobile are completely forbidden in my clean lab. I mean, it's good for your mobile and for the clean lab, because you know the acid vapor in the clean lab are corrosive for mobile. No mobile, no. And normally nobody talk to me. When I'm in front of my bench, when students came and say, "Oh, Mathieu," because I'm the head of the clean lab, sometimes they ask me, "Where is the cone? Where are the acids?" I say, shit, don't talk. Let me finish this step of the protocol, and I go to you. And also, I tell my students, also when they are on the bench, I say, nobody talk to you. Focus on the chemistry. And for sure, I can. Some people are not. I don't have the skill for this kind of stuff. People who are not patient, don't do geochemistry, because I have some master students. After 2 weeks in the clean lab, I told them, okay, stop. Do something else. Because you have to be very patient, and also you have to be very concentrated, because, for example, in the dissolution protocol, you are using very dangerous acid. And you can hurt yourself, but you can also hurt the other. Okay, with fluorhydric acid, we use 2 pairs of gloves. We are working in the hood with, glass gloves like this, glove box, and glasses, etc. And we are using very little amount of fluorhydric, 1 milliliter per sample. It's very dangerous. So this kind of protocol, it's published by Christian Pain. If you want to try, feel free. Okay, but is able to separate strontium, lead, lutetium, hafnium, uranium, thorium, lanthanum, cerium, neodymium, samarium in the same batch. It's not written in the publication how many days he needs to do this, okay? But he can do it. But you know, Michel, you know Christian Pain, he's a little bit... Okay. To finish, my objective is to get rid about fluorhydric acid in my lab. I have between 40 and 80 people working per year in my lab, and it's very difficult to watch out to be sure that they are not doing something very dangerous. You can have some accident, and HF is very dangerous. And so if you are not all the time there to supervise your student, the new master 2 coming into the lab. And so in Toulouse, we are starting to develop some new chemistry using a compound I showed you in the beginning, which is called ammonium fluoride. This compound is a solid compound. Okay? This is a synthesis between ammoniac, and HF. To synthesize it is very dangerous, but we are not doing it. But when it's synthesized, it's stable, it's not aggressive, and it's solid. And so if you put this in your powder as a solid, you close it, and then you put it at high temperature, it decomposes into HF and ammoniac, but it's in the closed system. You are not touching it. And when you cool it down, then you have no more HF, because HF is linked with the element which were present in your rocks matrix. So this is something we are at that time starting to develop, and we are also starting to develop some simultaneous purification of strontium and rare earth elements. It's a crazy paper published by the Chinese. They are doing some crazy stuff in geochemistry, because they demonstrate that on, for example, mass spectrometer, I will show you in my next lecture, you can measure on the same filament strontium and neodymium. And this is something we did not imagine some years ago. Normally, we completely purify our element to be able to measure them separately. But in fact, what we miss, the old isotopes, the old isotopic lab in Europe, conversely, in opposite to the Chinese, is that the machine, the mass spectrometer, are very, very performant now, are much more better quality, much more stable. and you can do some correction in the machine that we're not able to do in the past. And so this is also something we are now trying to optimize the time we are spending in the clean lab to have more time to do some research, because it's time consuming, okay, all this chemistry. And so that's the two application we are starting to develop in Toulouse to get rid about HF, especially for the student. Still, the senior researcher can still use HF, but I will be more confident if my students are using this, so I know they are safe. And also to perform some new chemistry, so totally different philosophy than Christian Pan did, okay, that purifying everything. Here the Chinese, they don't purify anything. They just separate strontium and rare elements and put everything in the mass spectrometer, and it works. Okay? So that's it for the clean lab. Maybe you have some question, or we make a 5-minute break so that I can drink something before switching to the mass spectrometer presentation. Okay? Thank you. Question? No question? Hmm? Thank you. In fact, I threw out the specific resin. In fact, I keep it. Sorry. Oh, yeah, I stay there. The specific resin, unfortunately, it's difficult to clean from one sample to the other. The Dowex resin, the organic one, you can keep them. The resin for neodymium, what we call the LN spec, we can clean them, but the specific ones are very difficult to clean, and they're also very expensive. This is why I keep them, and I'm thinking about asking for a student to make some tests about the possibility of cleaning them. But it's very expensive. The strontium spec resin, because they have the how do you say that in English? You cannot synthesize it. It's protected the way they are. And so I bought it 3 gram, 30 gram, and a pot of 30 gram of SR spec is 1,200 euro, and I use 0.3 gram per sample, and still I don't know how to clean it. So I store it. I remove it from my column, store it somewhere, and one day maybe I will make some tests. But you know, we are paranoiac, the geochemists. So if there is a possibility that this resin can, if you're reusing it, it contaminates my isotopic composition, then LN spec, normally I can process. I change it after 100 samples, and it's not expensive at all. In fact, I was doing it. I was synthesizing it when I was a PhD student. You buy a specific compound, you buy a Teflon powder, and you put this compound on the Teflon powder. You dissolve it in not alcohol, but acetone. And then you let it dry gently with a magnetic agitator, and the compound is sticking on the Teflon powder. And this is exactly, but now I can buy it, so I don't do it anymore. And the Dowex resin, I'm still using the Dowex resin I was using during my PhD 30 years ago, so you can use it for life. The other type of resin, all the organic resin are very stable. This is polymer, so it's very easy to keep in water. Store it in water, and then you keep for long. The specific one, all the resin made by the A-Chrome company, so what they call spec, SR spec, lead spec, true spec, RN spec, etc., etc. They are, in fact, the base of the resin is silica. You know, these medics you take as a silica to calm down your stomach. They are made of some silica gel, and in fact, this product is synthesized on this kind of silica gel. You can even buy the product, the base product, and do synthesize yourself, but the SR spec, I don't know how to do it. Okay, mass spectrometry. So, when you have beautifully and very cleanly separate your strontium, lead, uranium, hafnium, neodymium, whatever elements, you need to measure the isotopic composition. And you are not measuring the isotopic composition in your clean lab. You need a mass spectrometer. So what is the basic law of mass spectrometry? This is the Lorentz Force Law. So I don't know the way you are learning the Lorentz Law in India, but in France we use the finger like this in the secondary school, like the magnetic field, the electric field, and the force. It's exactly the principle of mass spectrometry. And this is why I missed my secondary exam, because I did all the exam with this hand. But I still am a mass spectrometer, a mass spectrometrist. Okay, so I will not go into the Maxwell equation, but specialty of my father, it's not mine. But I know the application to mass spectrometry. So the application of the Lorentz law to mass spectrometry is a charged particle with a certain speed entering into the magnetic field is deviated according to its mass and its charge. And the basic law is the ray of le rayon. Michel, tu dis comment le rayon en anglais? I know the diameter. What is the name of this? Radius. The radius. The radius of the deviation is given by the derivative of the previous, some derivative and linearization of the Lorentz Force Law, and you have the radius, which is given by this formula, 1 on the value of the magnetic field, square root of 2mv, so the mass, the speed, and the charge. So if you have isotopes of a single element, you have different masses of the single element. So if you are able to ionize, give a charge to your isotopes, accelerate them, give them a speed, and putting them into a magnetic field, you are able to separate them according to their mass. The basic of mass spectrometry. Okay. So when you see a mass spectrometer, it's a big magnet and a flying tube. A flying tube is the place where the ions are flying and are deviating, and the rest is a system to emit them, to make them, to produce them, and a system to collect them and measure them. But in the middle, this is the basic application of the Lorentz law, okay, an electric field, a magnetic field. Exactly like this. Well, Let's start with my specificity, the thermo-ionization mass spectrometry. This is the first machine were used to measure the isotopic composition, okay? Because the technology at this time was sufficient enough to build this kind of machine, stable enough to be able to measure. And you certainly heard about the ICP-MS, etc. But the ICP-MS techniques was really available in our lab in the beginning of the 90s. Okay, commercial machine. In a physicist lab, you have this machine before, but really in our lab, it was in the beginning of the 90s. So what is a thermo-ionization mass spectrometer? Thermo-ionization is because you are using a temperature control stuff. In our case, it's a filament to increase the temperature of the deposit of your element until you reach a level of energy where you can extract an electron from your element so that your element becomes positively charged. If you have an ion, then positively charged, then you can apply the Lorentz law. Because you have an ion, you can accelerate an ion, okay? You cannot accelerate an element if there is no charge. If you have an electric field, you can accelerate an ion, and then you can deviate it. That's the principle of thermo-ionization mass spectrometer. You have several types of mass spectrometer. The first mass spectrometer which were made were single collector. Single collector means you emit your element here. You have what we call an ion accelerator. So this is the electric field. Okay. You create an electric field. So the ion, as soon as it ionizes your element, is running away according to the intensity of the electric field. Then it goes into a flying tube, and it's deviated in a magnet. And so in the early time, you have only one collector. So if you have one collector, you have only one isotopes. You select the value of the magnetic field. You adapt the B here, this. You adapt the value of this, and you can change the radius. But still, you have one element in one collector. And so the way people were measuring the isotopes, and they were measuring a certain period of time on one isotopes, then they switch the magnetic field. They were measuring the second isotopes, switch magnetic field, measuring the third isotopes. Then you go back in the other way. And it's not that old because during my PhD, I did that for the rubidium, for example. And after, I take a grapher and I measure the peak. I make a interpolation between the way we are measuring like this and like this to measure the ratio between the two isotopes. In the beginning of the 80s, the middle of the 80s, you start to have what we call multi-collector machine. Multi-collector machine is you can have several collectors located outside of the magnetic field here, and you can, for example, select the position of the collector so that each isotope is entering on its own collector. Then you can measure simultaneously the ratio between the intensity you have in this collector and the intensity you have in this one. Much, much more precise in terms of measurement because you don't have time between the first measurement and the second measurement. Okay? This is why we can reach this kind of precision on this machine. The thermo-ionization mass spectrometer are known to be very stable and very reproducible because you control everything. You control the temperature, okay? You control the focusing, you control the electric field, you control the magnetic field, and you are calibrating the response of your collector. Of course, all this should happen in a very, very good vacuum. Okay? All these machines are under a very, very high vacuum, typically 10 to the minus 9 atmosphere. Why? Because if you have molecules of air in the flying tubes, the ion will shock with this molecule and will not cross the magnetic field to go to the collector. You will lose a lot of signal. Conversely, the problem with the thermoionization is the efficiency of ionization. Typically, you are emitting few % of the total amount of sample you have introduced in the machine, because it's not as efficient as other type of ionization process. This is my baby. This is my machine, brand new. We bought it 1 year ago, very expensive, and it was coming to replace the other mass spectrometer on which I have did my PhD, and which was still running. Not only it's very stable, very reproducible, but it's also a very cheap machine to maintain and very robust. So the previous one in our lab was installed in 1987, and it was the second installed in France. And this one was installed in 2016. It's been 1 year and a half. Okay, and the other one was still running. Of course, the number was not that good that what we can have with this kind of machine. So, according to the schematics you showed before here, source, magnet, collector, this is the source. The flying tube, you don't see it, but it goes that way behind. This is a magnet, typically 1 Tesla magnet, very heavy, 500 kilogram. And this is the collector housing, okay, here. So the path of the ion is they are ionized here, they fly into the tube, they are deviated into the magnet, and they are collected here. And one thing which is good is the computer is not in the place where the machine is. That was the case before, and you have the pumps we are doing the vacuum who makes you head like this, and so now the computer is in another room, modern. So this one is a new generation. It's made by Thermo Scientific, the former Finnegan company, and globally for thermoionization machine there is 2 companies, okay, making machine in the world, Thermo and New. The Thermo is German, but now it's American because it was bought by the. And you have a New which is from England. And there are some companies who are recycling your old machine to make them new, but it's not a new machine. This machine can measure positive and negative ion. This is a very specific particularity of this machine. So you can emit negative and positive ion. You may it run like manual, like in the ancient time. You are eating yourself, with the computer, your element until you reach a signal, and then you are measuring it. You can run in semi-automatic. You eat the sample, but then you press the computer and say, okay, now you measure. Or you can run it in full automatic. Put 21 samples on the turret. You tune the machine, then you press a button and say, goodbye, see you tomorrow morning. And you have 21 measures of the strontium, for example, isotopic composition. Of course, difficult sample, the sample with very low strontium concentration, you have to run them manually or semi-automatic and not automatic. This is for routine sample. So this is the schematics of the Triton. As I told you, the turret here, what we call the source, where you have the electric field. So electric field, it's 10,000 volts, minus 10,000 volt electric field, okay, to have a sufficient speed so that you can deviate the ion. You have some focusing unit. You have a valve here to isolate the source from the tube, because the tube is all the time under vacuum. You have some specific focusing stuff here to adapt the signal, you know, to calibrate. Thank you. And you have the collector here. On the machine in Toulouse, we have 9 collectors and what we call a secondary electron multiplier. Personally, I don't use all the collector at once. Only, if I'm correct, only one person in our institute is using the 9 collector ready in negative ions to measure the tungsten isotopes. But 9 collector, it's more than the number of isotopes for neodymium, for example. So, and in fact, you are interested by only one ratio. So, but still, you can use them. So, let's do some little bit technique. How you load a sample inside the machine. So the machine is under vacuum. So problem, huh? You cannot enter something when it's under vacuum. So what you need is to a place where you can isolate the machine. So there is a valve which can isolate the source from the tube so that you can open the source and change the sample. This is the source housing. Inside you have this turret with 21 position. Okay, this is the door, and so the valve is there. I isolate the rest of the mass spectrometer and I open this, and then I will start the measurement again when there will be equilibrium between the vacuum in my housing and the vacuum in my tube. So typically it takes, depending on the level of vacuum you need, but for strontium it takes 4 hours, for neodymium it takes overnight. Sample loading. We load the sample on pure metal filament. Of course, you want to measure the isotopic composition of your sample and not the isotopic composition of the filament. So you need very pure metal. We call them zone refined 99.9999% purified filament, and typically this one for neodymium we use rhenium. Very expensive. So it's tiny rhenium ribbons which are 2 millimeter wide and a few micron thick. And we are taking, you take out your beaker from the clean lab, you have a tiny solid of neodymium in the bottom of your beaker. You dissolve in 1 microliter of acid. You load it on the filament here with a micropipette. You load it here, tiny droplet. The width of a filament is something like this, 1.5 centimeters. With this kind of apparatus, you heat it gently until the filament is going, you know, you introduce a current here. So it's like a lamp, okay? You put a current, so the filament is glowing, and then the element is drying on the filament. You put it on the turret, you introduce it in the mass spectrometer. And then you will ionize your sample the same way. You are going to put some current here, well controlled, very stable, and when you reach a certain, the filament will go red, it's burning, and when the filament will reach a certain temperature, according to the ionization potential of your element, it's not the same for strontium, not the same for neodymium, not the same for samarium, not the same, if each element has its own ionization potential, it will lose an electron, and then it will be ready for mass spectrometry. Strontium, for example, typical temperature is 1,300 degrees. Neodymium is 1,800 degrees. Thorium is 2,000 degrees, etc. When I do osmium, it's rhenium. When I do rhenium, not on rhenium filament, is 780 degrees. Depends on the element, okay? No, Celsius. I'm French. Celsius. There are other than Celsius? Yeah, Celsius. So this is a geometry. For example, this is typically a neodymium filament. You have 2 filaments for neodymium because the problem is if you glow 1 filament here when there is the neodymium at 1,800 degrees, it will evaporate in a second. So what you do, you put 1,800 on what we call the ionization filament. So there is a media which is at 1 1800. So this one, typically, the distance is half a millimeter, and you are gently heating this one to evaporate your neodymium. So this one is typically at 1000 degree, and this one is at 1800. So when it's gently evaporates, it's ionized, and then it's extracted by the electric field. This is the source. Very easy to change, very easy to clean compared to the old machine, which was a nightmare. And here inside you have several lenses, and in fact the ability of the mass spectrometer is to focus correctly the signal. So it's like when you focus light, with a magnifier. It's exactly the same process. You have an ion beam instead of photon beam, and you play with lenses. In fact, I focus my signal on the z-axis, I focus it on the x-axis, etc., and on this one also, on the focal. So because what I want to do when I do measurements is to have the maximal signal, okay, the maximum signal divided by compared to the noise. Maximal signal on noise. So I focus it so that I am focusing my beam really in the center, so I know that I will have the maximum signal in my collector. So you have several lenses here. I will not describe the different lenses. You have one which is the extraction one. Extraction is the one which minus 10,000 volts. Surely you don't want to touch it, okay? But normally it's disconnected when you open the source. But I know one guy who touched it, and he jumped out from the room, from here to the wall, with the hair like this. Still alive, huh? Maybe he's not really good in his mind, but it's still alive. Okay. Then you have a flying tube, okay? And you see the different isotopes separate according to their mass, because the radius is proportional to the mass. And if you are clever enough to put one collector in front of each mass, then you can measure all the ratio you want to measure. Okay? And it's very, very precise, because when you emit elements here, they all reach the geometry. It's like you're on the racing, on the racing stuff. They all reach the collector at the same time. So you're sure that your ratio is really proportional to the ratio inside in the source, inside your sample. Typically, this is an image of the collector. So everything is under vacuum, something normally you don't see. You have all the collector are mounted on some motor-controlled stuff here, and so there is with the computer you can say, okay, you go to this position, you go to this position, and so when you receive the mass spectrometer, you have to calibrate all the position according to the different elements you want to measure, because of course the distance between the collector when you do strontium, when you do neodymium, when you do whatever, will not be the same. Okay. We call the collector the Faraday Cup. In fact, the collector are made in graphite, and this is very simple idea about when the ion is hurting the graphite, it produces a spark, and what is a spark is electricity. And in fact, you are measuring electricity in the collector, or in fact, because there is very little spark, you are measuring a deviation to a certain electricity, a certain current you are applying on your Faraday cup. And so if you receive 10 million ions, then you will have a deviation of 10 million spark on the electricity you put at the beginning. That's the principle of measurement. Of course, to be able to really measure this signal, you must have a very high resistance behind the Faraday cup, and so the why this machine is very expensive is 600,000 euro, because of the technology which is behind the Faraday cups, behind the amplifier, behind everything which is able to measure very tiny signal. Okay. There is some process also, you can deviate the signal to put the central cup to put in the ECM, but I don't want to go into this now. So this is how you can, if you unmount and you see the interior of the Faraday Cup. This is graphite, typically just a graphite outing with a tiny hole here. The ion beam is coming inside, earthing the graphite, and then producing current. And you're measuring the current. This is an SEM. I present the SEM because this is typically used in ICP-MS, so you should know what it is. Exactly the same process, but you have no graphite. You have electrodes with different charge, and the ion is coming there. The signal is amplified. It emits secondary ions. Then it multiplies, emits secondary ion, and in fact, with this kind of process, a chain of D node, you can measure very, very little signal, and much more and much smaller than what you can measure with a Faraday Cup. And this is typically the kind of system you have in ICP-MS. But still, we have one in the mass spectrometer. For example, people measuring the 230 to 32 thorium. 230 is very, very, very little abundance. And so we are measuring the 230 on this kind of apparatus and the 232 on the Faraday Cup. Then you need a software. So the amplifier are here in our mass spectrometer, Faraday Cup are here, and you need a software because you need to tune your machine, to tune it, to develop some method specific to the system you want to measure. So normally it's done by me or the engineer, and when somebody is coming to do some measurement, the method is directly available. But if you want to measure some specific stuff, like for a very low abundance neodymium in peridotite, then maybe I will change the protocol and we will discuss together to adapt the methodology and the software to your specificity. Or you want to measure another type of isotopic system, then we will discuss together and try to find what are the best position for the cup, what are the best type of filament you want to use, and what kind of time you want to measure according to the signal and the noise, etc., etc., etc. Mass spectrometer guy told about peaks. We always talk about peaks because the signal, when you see it on a window, either ICP-MS or TIMS, will be like this. And the scale here is the mass, okay? It's centered on the real mass on the isotopes. So when it's not 87, okay, for strontium, for example, the real mass of strontium, 87, is 86, 9, 8, something. And we go from 87, for example, here, 97 to 87, 98. Okay, this is very precise centering on the cup. And then you consider that the machine is correctly tuned when you have a flat peak and you have a large space to measure the intensity of your peak here. This is a very good measurement of calcium. You know, all the peaks are centered and all are flat. Of course, so as I told you, I have one specific isotopic system with a different method application. And the main, so this is typically a signal on mass spectrometer. You hit with your filament gently your neodymium or strontium. Here I think it's osmium. You hit it. Sometimes you calibrate it to check if your focusing is correct, your mass is really centered. Then you continue heating. This is the focusing here. You focus until you reach a level that is sufficient enough for you to have a good measurement. Then you launch the measurement. And typically, the measurement is divided into blocks. You measure 10 times, 15 times the peaks. Then you stop. You make a sort of recalibration. And then you continue. Typically, in my machine, neodymium heating will take 15 minutes, 20 minutes. And the measurement will take 40 minutes to have a right number. Strontium a little bit less. Then there are many corrections that you have to apply to the signal, and this is tricky because this is the job of the mass spectrometer metrist to correctly to calculate correctly the interference, etc. you can have on your signal. And the major correction you have on the mass spectrometer, because when you look at the ratio at the end, it's not the ratio you should have on the nature. They are affected by what we call mass fractionation. Mass fractionation, you will hear a lot about mass fractionation if you are working with isotopes. Mass fractionation is typically maybe what you have learned in evaporation in lakes. The light isotopes are fractionating, are going away first, for example, for oxygen when you are evaporating, and the heavy isotopes are going after. For example, oxygen 15 is evaporating first, and then it's followed by oxygen 18. This is the same in the mass spectrometry, the mass spectrometer source. You are emitting the light isotopes, and then gently you are moving to the heavy isotopes. Of course, you are emitting all the isotopes, but you are emitting more the light isotopes. So we have what we call a mass fractionation, and then we need to correct from the mass fractionation. For a system like neodymium or strontium, it's very simple. It's simple because we have stable isotopic ratio. Take the example of strontium. 84, 86, 87, 88. What you want is this one, 86 on 86. So the machine is able to give you this number without any problem, but it will be wrong because mass fractionation, you are going to emit more 86 than 87 because you emit the light isotope first. But this property of the emission is the same for the other isotopes. And the other isotopes are known. They are not radiogenic. You know them. So you know perfectly what should be this ratio here. Okay? Exactly. It's 8.37 something. And you know that you should get this number. And if you measure it with your mass spectrometer, you are measuring, you will get 8.29. Then what you have to do is just to apply a correction so that you bring this one to this one and to apply this correction to the other isotopic ratio to correct from the mass fractionation. Okay? So typically in the teams we apply an exponential correction, not a linear one, because it has been shown that it's better for the correction. So for all the isotopic system where you have the chance to get a stable isotopic ratio, strontium, neodymium, hafnium, etc., you can do with this kind of what we call internal max fractionation correction. For lead, you can't, because for lead, you have 4 isotopes, 204, 206, 207, 208. This one is radiogenic, this one is radiogenic, this one is radiogenic. There is no stable ratio. So you have a problem to correct for mass fractionation. So in the early days, what I learned when I was in PhD, the only way to do it is to run a standard. Okay, so here you have the 208, 207. To run a standard where we know exactly the isotopic composition, then you put it on the fractionation line. This is the real value. This is what you measure, and then you will calculate how many the number you have to multiply this to go to this, and then you are going to apply this number to your sample. It was not that good, but this is the only way we can do it. And now there are some other way to correct, adding spikes, and there is what is called the multi-spike method, double spike, triple spike method to correct from lead. And so we are able now to get very good number for lead, but I will not go into the detail of this now because the calculations are terribly complicated. This is the basic. The second type of correction you have is interference correction. Okay, this is something we can calculate. The dark noise, like in other apparatus. All apparatus you are measuring, you need to subtract the signal. And you will see in ICP-MS you have some other correction to do. So the base of mass spectrometry, good mass spectrometer measurement is you have to be reproducible. You remember when I talked about statistics yesterday? We are measuring every day a standard, not a rock standard, a neodymium standard if you do neodymium. Every day we're measuring a standard. And we are making some mean and standard error deviation of our standard to check if we are still measuring correctly. And if you start in the morning, you measure the standard and the standard is completely wrong, you stop. You call the engineer or you call me and we check what's going on. But never measure your rock if the standard is not correct. That means that the machine has some problem. Okay. The second way to measure the isotopes is with a plasma source mass spectrometer. So you remember what you have to do to apply the Lorentz force is to transform your element into ions. In the TIMS, in the thermo-ionization mass spectrometer, what you do is you heat it up gently on the filament. On the plasma source mass spectrometer, you throw it in the plasma. And plasma is so hot that it will be transformed into ions. So typically, the machine, like for TIMS, there are two machines in the world who are measuring isotopic ratio with a plasma source. One is built by Thermo, same I have for TIMS, and the other is a new. They are the two competitive companies. Okay. In fact, this machine, Neptune, we have also one in our lab, share a lot of components and a lot of parts with the Triton. Okay, only the source is different, and I will show you there are some tricky also change in the machine. So again, you can have single and multiple collector machine. Single collector are used for trace element measurements. Okay, and normally they are not so complex. You don't need a magnetic field, but this is not my topic today. You can measure multi-elemental isotopic measurement because, not like for TIMS, you can throw all the elements in the plasma. You don't have the problem of ionization potential because the temperature is so huge that you can ionize everything in the plasma. Normally, if the machine were perfect, you can throw your strontium, neodymium, lutetium, lead, everything inside the machine, and you should be able to measure all the isotopic ratio. You tune your collector, because all will be ionized at the same level, more or less. Okay? Of course, it's not the case. People think about that at the beginning of the ICP-MS, but it's not the case. You still need to purify. Because I'm a TIMS guy, these machines are less stable. I prefer my machine, okay? Because the plasma is just, I finish. Plasma is, by definition, is unstable media, okay? A plasma is like in the sun. Sun is a plasma, okay? It's a mess. But it's very powerful because it has an ionization capacity, which is almost 100%. All you are going to inject in the machine will be ionized. So, on the opposite to TIMS, you are able to measure a ratio on very, very, very low level. Okay? So, how do you introduce the element in your machine? So, except from laser, but the application for laser on isotopes are not that developed yet, still are in development, so I will not really focus into laser. I will switch to a solution-based introduction system. So on the plasma, the way we're introducing the element is not a solid that we load on the filament, is we have our purified strontium, neodymium batch into solution. And we suck out, using a capillary tube here, we suck out the solution and we introduce into a spray chamber to transform this water, or slightly acidic water, into very, very tiny droplets, very tiny, so that they can burn into the plasma. And need to spray, like, air spray, same. So, but the gas which is used to spray is argon, because argon is the main gas used in ICP-MS. This is a typical spray chamber. So you have an injector. This is the spray of your air spray. Okay. Here your sample is coming. If you have the gas which is pushing the solution into the spray, and this spray is sent into the spray chamber. And the objective of a spray chamber, you see it on these schematics, is to remove the heavy droplet and only to keep the tiny one, so that first you are not going to wash out your plasma because you send water into a flame, and the ionization efficiency will be very good because the droplets are very, very little. So typically your sample is dissolved in nitric, very diluted nitric. It is a nebulizer, okay, spraying into the chamber, and all this is carried out into the torch. Remember that we are at 1 atmosphere. We are in the air. We are not still in the vacuum, okay? And you remember the Lorentz force, the blah blah blah, ion trajectory, etc., should be under vacuum. Still, there is no ion here, okay? Only element. Then you reach the torch. Torch is a plasma torch in ICP-MS. Temperature is between 7,000 and 10,000 degrees Celsius. Of course, there is a big gradient between the center of the flame and the border. So, because you don't want to melt your mass spectrometer, you have to cooling down very efficiently. This is why we are using a lot of argon in an ICP-MS. Argon, very pure argon. And this is why an ICP-MS measurement is expensive, because we are using like 20 liters per minute of argon. But the majority of the argon is used to cool down the machine. And so the injector, here you have your spray chamber. The injector is bringing the very tiny droplet right into the heart of the flame, okay? And how you are creating this plasma flame is with a very intense electromagnetic field. So in fact, your argon is in the middle of a very intense magnetic field, and if we inject a spark, then you have a plasma which is maintained by the magnetic field. Plasma is a media which contains argon plus, and electron, and all the time it's changing from one to the other. And if you inject your element inside this, at this temperature, all are ionized. Then you have ions, but you are still in 1 atmosphere with air. You need to bring all these elements inside a mass spectrometer with a vacuum 10 to the minus atmosphere. This is the tricky part of the ICP-MS. To do this, you are using the property of a supersonic signal. This is something which was discovered when the first supersonic jet reached the level of sound. They realized that behind the wall of sound, you have a zone with a certain vacuum. And so this is exactly what is used in ICP-MS. You are throwing your ion beam at a supersonic speed, so that here you have a zone with which is under vacuum. And you create an intermediate vacuum, and the way you do it, you have 2 cones with different geometry. We call it the interface, And in fact, the ion beam is collected within this interface. And thanks to this, you can switch to 1 atmosphere to 10 to the minus 9 because of the supersonic property of the ion beam. Okay? Of course, all the ions are entering the mass spectrometer. It's a lot of signal. It's a lot of mass. And also you are introducing photons inside the mass spectrometer. And all this, and sometimes electrons too, all this can damage the machine. So you have a lot of lenses to filter this and to keep only the signal which is interesting to measure. So you have a photon filter to remove the light. You have a combination of lens and quadrupoles to focus the signal and to get rid about everything which is not useful for your measurements, okay, to focus it. The focusing unit is much more developed than in a TIMS mass spectrometer. This is typically a quadrupole filter. In the Neptune, also, the machine I show you, you have this slit, entrance and exit slit, which can select part of the signal. And maybe I will not enter into the detail, but it is to get rid about some interferences you can have in the plasma, because the problem in the plasma is your recombination between some elements and the argon and the oxygen. And if you want to measure for example, this is a typical example we use to explain the interference. If you want to measure the iron 56, you can measure this element, but the machine will also produce this 56. So when you are measuring, because you are in the plasma, and the plasma ionizes everything, and the plasma also is argon plasma in atmospheric pressure, if you produce this, it will be accelerated the same way in the machine. It will not be filtered by this because it's 56. And so when you are measuring 56 iron, you are measuring the sum of this and this. And this is the tricky problem with ICP-MS. We are creating a lot of oxide and argide interferences. So the first way to filter this is what we call the electric sector here, or is a ACA filter. The ACA filter, in fact, is a sector where you apply some electric field, and the ion with a bad energy will be removed. The one we are going too slow inside the machine, they will not go out. They are too slow. They are removed. This is the first way to remove the bad ions. Okay. When you have filtered this, it's called the electrostatic energy analyzer, but in fact it's just an electric field. This is simple. The ions are coming. If they are too slow, they will be trapped by the electricity on both sides. Then, after the electrostatic energy, you are in the mass spectrometer with the same geometry, and in fact it is the same as you have in the TIMS, in the Triton. Then, what you have to do is to focus it using the magnetic sector, exactly the same than before, and then collecting in the collector. So the Neptune, the MC-ICP-MS, have the same magnet and have the same collector as the Triton. The big difference is the only way to accelerate an ion beam in a machine which is at start at atmospheric pressure is to put all the machine into minus 10,000 volts. Okay? Otherwise, if you not do this, then you will have electric arc everywhere. So the Neptune, when you see it, it's completely covered, it's completely protected because all the machine, all this, it's at minus 10,000 volts. Okay? That's the big difference between the teams and the machine. So, and even if you have filter with the electrostatic filter, if you have separate them with the mass, the ion here, with the same mass, will reach the collector at the same place and at the same time. So we will have to deal with oxide interferences. Okay? Some you can solve them using, for example, the slit I show you in the beginning. Some are not. Typically, the rare earth elements in this kind of machine, if you have oxide interference, for example, the light rare earth elements on the heavy rare earth elements, you cannot solve this with the geometry. Or you have to calculate them, or you have to estimate them, and then you have to make offline correction. So you remember, oxide and argide are the main compound you can create in a machine. All can recombine. Okay. The high resolution, so this is a tiny slit, can solve some interferences, but not all. You can still, like for teams, resolve the mass fractionation correction using the stable isotopes, but with the multi-collector ICP-MS, you can also add some elements which have roughly the same mass, which are sitting, for example, in the middle of lead, and use the fractionation on this element to correct all the others. Typically, we use thallium. Thallium has 203 and 205 mass. Here, sitting right in the middle, we measure the fractionation thallium, and we apply this fractionation to neodymium. This is something you cannot do with the TIMS. So here you have a list of the kind of interferences we can find. So if you don't separate them, so for our case, if you don't separate the rubidium from strontium, they will fall on the same mass, and you have trouble to measure them. So now people are trying to develop the same type of measurement on isotopes using laser ablation. Okay, but the problem is to reach the 5th digit or the 6th digit on the isotopic ratio with a laser ablation when you have a little amount of element going into the system, and to stabilize it also. Solution, you can run it for long and then stabilize. Laser, the problem is pulsative measurement, and so it's difficult to reach the precision we can get with solution-based measurements. And to end, some entertainment about of this machine. I have some video. Normally they should work. Of course they don't. So I will show them to you using to show you how the signal behave inside not this one. Still have some music.
Follow the journey a sample takes from its sample vial through the ICP-MS to the detector. Sample is pumped from the sample vial into the nebulizer, where it is mixed with argon gas to form an aerosol.
Everybody listen?
Larger droplets are removed from the sample aerosol as it passes through the cooled spray chamber, and the fine aerosol is swept into the central channel of the plasma.
So this is for a quadrupole, not for a
temperature argon plasma. The aerosol droplets are dried, decomposed, atomized, and finally ionized, producing a rich source of positively charged ions. The ions are extracted from the plasma into the interface through the sampling orifice, and then through the skimmer cone into the high vacuum region containing the ion lenses and mass analyzer. Electrostatic lenses focus the ion beam and
this is a quadrupole. I did not speak about it.
Unwanted neutral species by bending them into the reaction cell, the heart of the octopole reaction system, or ORS. The ORS is unique in quadrupole mass filter and are separated based on their mass to charge ratio. Only the target ion is stable and passes along the axis. Only the target ion is stable and passes along the axis of the quadrupole. The quadrupole scans rapidly across the mass range and passes
we don't have the end of the movie.
Sequentially to the electron multiplier detector.
Sorry.
Ions strike the detector, and the resulting electronic signals are processed by the detector electronic.
So sorry, the end of the film does not work, but I have another one. Hope it works better. I was working on my computer. Still music, huh? So this is what we call a pump here to bring the signal to the. Then this is a plasma where everything is ionized. That's the wire of the electromagnetic stuff, which then you reach the interface. These things can get very dirty because all the signal is flowing here. So we change them very often. Then can be a nickel, platinum, etc., etc. So this is the ESA filter. This is the focusing quadrupole. Oh, dirt. So the quadrupole is effectively shaping the signal. This is a magnet when you have separation. Everything is a game of focusing in mass spectrometer. And the principle of mass spectrometry. This is the specificity of this machine. So this is for concentration measurements, okay, not ratio. The normal ICP-MS, the basic one, you do concentration analysis, okay, not. This is a commercial. That's a quadrupole. So this is the way to select from different mass, not using a magnetic sector. Using the property of vibration of the ion, you select the frequency and the tension on the quadrupole, and according to this, you can select different ions. Definitively, it's not used for isotopic measurements because it doesn't give you beautiful peaks to measure the intensity of the peak. Sorry, it's a commercial movie. Huh? It's a shame that they did not show the. Okay. So do you have questions? You want to see the movie again? Yes.
We have ICP-MS machine. So for that, let me, how can I make the use of ICP-MS?
Sorry. Yeah, come back to the question, please. Optic ICP, it's different. There is no signal entering the machine except the light, the absorption ray. The ICP-A, yes, it's different because you are not selecting the element according to their mass. You are selecting the elements according to their emission rate when they are going down from excited level to they reach the level. They emitted energy, specific ray, which is specific for each element, and then you are measuring this, but not mass. No signal is entering the machine with an ICP optical ICP. Yes, you can use ICP, optic ICP. Yes, my topic was to deal with radiogenic isotopes when I come to Pune. So I present you radiogenic isotope. Optical ICP is another way to measure the trace elements. There are many ways to measure the concentration, but with optical ICP, you never deal with isotopes. No isotopes, only elements. Okay? The optical ICP is not able to make the difference between the 86 strontium and 87 strontium. It will measure strontium, only strontium, concentrations. Okay? It's a good machine. No problem with the optical ICP. You can make very precise measurements. Not so low. You cannot measure concentration as low as you can measure with a mass ICP-MS, but still, it's a very good machine. But far from the isotopic subject. Yes. Yes, because the property of the ICP, optical ICP, is because there is no mass flux inside the machine, you can measure a very large range of concentration, from percent to ppm. With an ICP-MS, concentration, I mean, you can measure only very little signal, because the collector are calibrated, are made to measure very tiny signal. So you cannot measure major element with ICP-MS, otherwise you have to dilute them for And also about lab concern, I told you about the price for a clean lab. It's half the price for an ICP or a Teams lab. Teams lab is even less. And what you need is a good power supply. Electricity has to be very good. You need a dust-free environment, but not 10,000 stuff. You need temperature control, because these machines are producing heat. Okay. And exhaust system for the argon supply. But it's typically what I told you. We are designing a new lab, so in Toulouse, It's 1.4 million for the, but it's a big one, huh? So it's 160 square meter. 1.4 million euro for the clean lab, and 600,000 euro for the ICP-MS lab. So also very big ICP-MS lab. So if you want a tiny one, you can reduce the price. But still, except if you want to work on meteorite, then you have to have a very isolated environment. But for normal geological sample, my team's lab is in a place where you have air conditioning. Of course, you don't open the window for the dust. You have a power supply, and what I need is air pressure. That's it. Of course, if you want to work with negative ions, you need oxygen leak, but this is not something very expensive. Because everything is inside the machine. Okay? All the measurements are inside the machine. There is no very difficult way to contaminate your sample when it's inside the machine. In a clean lab, everything can contaminate your sample. Dust. No fan, for example, in the clean lab. Huh? Cone, yeah, we change them, yeah. Or the cone, also when you open your solution with your sample and you put it on the eye machine, normally it's on a protected box with a filter, so that the dust from the room is not entering your sample. But you know, measurements are fast, so to contaminate sample, even here, if I put my sample on the air, I need hours to contaminate my trace elements. You know, it's water stuff. The time is the dust to be in the water, to be dissolved, and to be ready to contaminate my sample in ICP-MS, you need hours. And normally, when you are measuring your sample, you are measuring like a lot of sample per hour. So, but still, a clean box is needed. Also, people have clean lab in France. There are some little university. They have their own clean lab, small one, okay, in their university. They are doing their separation. Then they come to Toulouse or to Clermont-Ferrand or to other lab with their beaker. They book the machine for several days, and they do their isotopic measurements. You should know that you can buy some portable clean lab. There are some manufacturer in the world. When you buy a bench, like you put it on the bench, stuff like this, like the width of this, and everything is set up inside. You have a place for your hot plate, you have a place to store your acid, you have a clean air flux, you have a place to do your column separation, and you bought it, you can set up it here. Of course, you will have to change the filter very often, so it's better to put it in a closed place, but you can put it in the bench. If you don't have the money to totally design a clean lab, you can buy this kind of bench, okay? There are 2 or 3 companies. It's a portable clean lab, okay? Typically what they install on boat, what they're installing, the kind of lab they install on boat or close to some mining stuff or whatever. They want to do some measurements and they don't want to design a clean lab. They bought this kind of stuff and you have everything. You can do your preparation. I had some colleagues who have this in the US because they cannot afford to have a complete a clean lab, and they are the only geochemists. So you won't design one lab for one geochemist. They bought this, they put it in a room, they do their separation. Then when it's done, they go to the next university, they make their measurements, and it's okay. But in Toulouse, we have 40 people asking for the clean lab, so we cannot buy 40 portable lab like this. Okay. I hope one day you will come to visit. You will come to Toulouse, sorry, to visit our lab. Huh? Yeah. The reputation of your lab, you make 20 years to have it. A good reputation, it takes 1 week to lose it. If somebody recognizes that your data are completely wrong, say, oh, Toulouse, they are working like shit. And then it takes 20 more years to come back to say, oh, no. So I can sell some standard. I took my hat of seller. I'm in the International Association of Geoanalysts, and we are selling standards to intercalibrate the lab and also to make a round every year. We send sample twice a year, random sample, can be anything. You dissolve them, you measure them, whatever you can measure, trace elements, major elements, isotopes, not that much, but and you send them back to us. And it's anonymous, and then we are sending back to you a spreadsheet where you can see that you are good or not in terms of measurements. And for example, you are measuring correctly the rare earth elements, but for example, you are very wrong for cobalt. Then you have to come back to your lab and say what happened, why I'm so bad into cobalt, etc. And it's very good for intercalibration, and very good also, it's a self-confidence for your lab that you are measuring correctly. Yes. Yeah. No isotopes. We are starting to do it for isotopes, but for isotopes, radiogenic one, there is no international standard. So the problem is we start for lead but we are sending glasses, artificial glasses, where we are sure that, especially for dating, that they are correct. But for radiogenic isotopes in rocks, this is very difficult because the homogeneity of the powder has to be very, very good. And the way we are doing with isotopic ratio is we are measuring a standard, artificial standard every day. And when sometimes students who are not mine come to the mass spectrometer with rock standard, but because the supervisor did not know about isotopes, they say, you dissolve the rock standard and then you separate the isotope. I say, okay, we can measure it, but there is no significance because there is no accordance about the right isotopic ratio of this standard. So even you cannot use for publication. And even the very, very, very well-known geostandard like BHVO2, which is very famous, you cannot use it in a publication to prove that you have measured correctly your isotopic composition for neodymium. You still have to use the international La Roya or GNDI or Merck or whatever, which are artificial standards.
have a lot of cars, a lot of detecting. So you have to be sure that your lab is clean and is very close things toward no contamination like gas and dirty, because you are looking at the red isotope content with 1%.
This is why we are measuring a blank in isotopes. Typically, when somebody asks to come to the MS facilities with some sample series, because I'm not supervising all the isotope separation, I say you should have a blank, and you should know your concentration. Okay? Because if you put too much strontium in the machine, it can damage the collector. If you have not enough, you are not measuring correctly. So I discussed with students before, during the pause, and I say normally what I do is I dissolve my sample, like the way I show you before with acid. And then when I have dissolved my batch of powder, I select a little bit for trace elements. I use the rest for the isotopes. So I'm sure that I have the same, I have the two information on the same dissolution batch. So if there is heterogeneity in my powder, then I get rid of this. Because you remember, a powder, if you crush a granite, your powder here will be a mixture of grain of biotite, Carfelspore, plagioclase, maybe a pyroxene, etc. Are grains of this. So if it's not homogenized, if it's all granite and you select a part which is biotite rich, then you will get a very radiogenic isotopic composition, which is not the real isotopic composition of your powder. So the homogeneity is very important. And a way to get rid of this at the first level is to measure the concentration and the isotopic composition, so that you have a consistency between the rubidium strontium and the strontium isotopic composition of your batch. Of course, I prefer that it's homogenized, so that it's reproducible. But still, for osmium, it's a nightmare. Osmium, for example, in mantle rocks, osmium is carried by the sulfur, by the very tiny alloy in your mantle peridotite. And then homogenization is a tricky problem, to be sure that you are measuring. It's not the silicate. It's not in the silicate, the osmium. So when you are measuring powder, you need to be sure that it's really homogenized. This is why while we are doing osmium, normally we dissolve 1-2 grams of sample. So we try to get rid about this problem of powder heterogeneity. Question, no question? And to learn mass spectrometry, to learn this kind of my job, there is no university courses specific. The practical stuff you have to learn into when you are in the lab, because it's not chemistry. No chemists think we are bad chemists, because it's not pure chemistry. It's not geology. The normal geology say we are crazy to spend all the time in the clean lab, with acid. And so the way I've learned geochemistry is, I came the first time I was a master student. I came into the clean lab, and there are other students, postdoc, researcher, and they teach me the protocol, which were most of them home design. And I learned little by little like this. I learned the first time I was on the mass spectrometer. Because mass spectrometry, you have many types of mass spectrometer. There are one specific type devoted to geochemistry, so this kind of study. And I learned with the technician and also one of the researchers. They told me about the basic. In fact, I'm still learning about the technique which is behind the machine, because the machines are changing. We have a new generation of machine. Inside there are new generation of electronic, etc. I'm not an electrician, but I like to know how it works. To have an idea about what kind of level I can reach in the precision of my measurements. And so I'm still learning. Even in the clean lab, I'm still developing, learning, etc., etc. So really, you have to put your hand inside if you want to do this kind of measurements. It's not my lecture who have transformed you into an isotope geochemist. I'm sorry.
कसे सुरू करायचं? Okay. So good afternoon. So we've been discussing about the interior of the Earth, and we've been making various different proxies, using different proxies to understand the Earth's interior as such. And in most of the cases, we had discussed more about the mantle xenoliths and their chemistry as such. Yesterday, Michel spoke about the evolution of the subcontinental lithospheric mantle in the cratonic region, especially the Kappa-Oval craton, and wherein to a great extent how the xenolith population to an extent can be made use of, and its chemistry to understand how the subcontinental lithospheric mantle has evolved in the Kappa-Oval craton. So here I am giving you an Indian case, and especially the xenolith bearing alkaline magmatism that is commonly been seen present in the Kutch region of Gujarat as such. In fact, this was a PhD topic of Raman Durai Swami under my supervision. So most of the work basically that was done was a part of his PhD thesis, and way back almost 10 years before time perhaps. Okay. So here we are going to look at the alkaline magmatic activity. And of course, you all know that during the other lectures I have spoken about that basically the most of the Maharashtra region, state of Maharashtra, is made up of Deccan basalt, and the evolution of the Deccan basalt to a great extent is attributed to the presence of a mantle plume, the reunion plume as such. Okay. And to a great extent associated with this large igneous province, you have the other variety of rock types, which include basically the alkaline magmatic rocks, and then there are some acidic effusives also. Okay. I am going to concentrate more on the alkaline magmatic rocks and not on the Deccan tholiites, because tholiitic magma generally is stored at the subcrustal depth in the magma chamber. So during the magma chamber basically it undergoes fractionation, differentiation processes, and therefore it becomes a little difficult from that particular magma to understand about the source character. You definitely can do it, but you have to do the reverse engineering basically. You have to go on minusing the effect of fractionation, minusing the effect of basically differentiation, and so on and so forth as such. And instead, therefore, I am targeting the alkaline magmatic rocks. The reason being basically they are highly mobile magmas and generally are rich in volatile contents, and therefore their travel time is comparatively smaller, in the sense the speed with which they come from the interior to the surface is much faster, the velocity with which they make their appearance on the surface, and therefore there is hardly any time for the magma to get equilibrated with the crustal material as such, or the sublithospheric mantle. And that's perhaps the reason why the speed and basically the high volatile content, whatever that come in its way is been brought to the surface. So those are the rocks basically which to an extent should be looked for the occurrence of mantle xenoliths, occurrence of crustal xenoliths as such. And this is the case basically of the Deccan volcanic province. Generally, if you look at the Deccan volcanic province, as is a vast province, more than 500,000 square kilometer, that is the present distribution, whole of the state of Maharashtra, part of Gujarat, part of Karnataka, part of Andhra Pradesh. So that is what is the distribution. But the dominant lithology that we get to see are the tholiitic basalt. And the effusive alkaline magmatic rocks basically are confined to very small narrow regions onto the coast, especially to the south of Bombay in the region of Murud and Janjira close to Alibag, and the other basically is the area to the north of the Narmada zone region, especially in the Kutch part, the Cambay Rift, what is it called to be, so where they are present, and there also the volumetric proportion is very small. They generally occur in the form of small plugs or sill-like bodies or dikes or sheet-like bodies. But interestingly, many of them actually seems to be entraining both xenolith as well as xenocrystic material. So you have a combination of both the host rock and the xenolith. So whether with the xenolith to an extent can be used to understand first of all how these alkaline magmatic rocks are derived, whether they are from the same source or something else has happened. So that is the way basically this particular problem has been tackled as such. Okay, and this is what we will be looking at. So if you believe in the plume hypothesis, obviously during the Cretaceous time, the Indian plate, which was moving northwesterly basically after its separation from the African subcontinent as such, and then it moved over the Reunion Island, which is presently situated to the south of the Indian subcontinent in the Indian Ocean as such, and during its basically passage over, it has moved over the Reunion hotspot. If the hypothesis is correct, then in that case the oldest rock should occur to the north and the youngest to the south as such. And generally, if it is a plume related magmatism, in case of plume normally we believe that plume is not a homogeneous structure, more or less it is made up of different layers. So on the very top normally you have a thin small envelope of enriched material. Then the middle body of the plume is generally made up of both the mixture of subcontinental lithospheric mantle and the enriched mantle. So depleted and enriched, that is the combination mixture that you get to see, and the tail part again is basically is the enriched lower mantle. So this is how basically you get to see the plume as a layered structure, and melting of these individual layers would perhaps produce different types of rock. So on top, the enriched envelope, enriched with volatile content also, is actually the source region for most of your alkaline magmatic activity. Then the middle portion, which is mixture of the depleted and enriched mantle, would perhaps basically give rise to the large scale tholetic magmatic activity. And if the magmatism or melting continues further in the tail part, the stem part of the plume, perhaps you would again get to see presence of alkaline magmatic material coming out as such. And this is what we are trying to test if the reunion hypothesis is correct or not. Okay. So at least distribution wise, the alkaline rocks are seen present to the north of the main province of the Deccan volcanic province. They are seen situated in the region of Gujarat, both in Saurashtra and Kutch region as such. And generally, the trajectory continues. In fact, there are people who are reported rocks all the way from the Suchar zone, which is lying further north from the Himalayan part, where they are recorded ages of the order of some 110 or 90 million years and so on and so forth. And intermittently, there are sporadic occurrence of alkaline igneous rocks. For example, the various alkaline intrusion that we speak of, whether it is the Girnar complex, whether it is the Sarnu-Darnari complex, whether it is Mundwara complex, or the Fenaimata complex, or the Ambadongar igneous complex, all those are to an extent part and parcel of this large igneous province. Only the dates are differing. Some of them are younger to the main tholetic flows. Some of them are older. Some few of them are seen intruding into the main complex. Some are basically prior to the emplacement of the Deccan tholiids. So to a great extent, basically, generally world over it has been seen when there is a plume related magmatic activity, like for example the Hawaiian island that we speak of, or Hawaiian magmatic province that we speak of. The precursor is alkaline igneous activity, then you have tholetic magmatic activity, and then preceding the tholetic activity again you have alkaline igneous activity. So generally this is what is the sequence. main phase of tholetic activity is seen sandwiched between two alkaline episodes, one older and one younger as such. And perhaps this represents an older than basically your Deccan volcanic or Deccan tholioids as such. So this is what we are going to look at during this particular lecture. So the objective of the study, as were outlined for the thesis part as such, classification of the alkaline host based on the mode and bulk chemistry, the modal mineralogy as well as the chemistry basically. Based on petrography and mineral chemistry, comment on the petrogenic aspects of the ultramafic xenoliths, because xenoliths are part and parcel of these magmatic rocks occurring as basically fragments of the mantle entrained in these rocks. So whether there is any interaction between the subcontinental lithospheric mantle and the magma that is produced, that needs to be looked at, and for that purpose the xenoliths been used as proxies of the source region. Then third, based on the mineral chemistry, determine the PT conditions. So put temperature pressure constraints at what depth basically these xenoliths from where they are originated, at what temperature and at what partial melting this particular residue has been produced so as to get entrained into the alkaline igneous activity. Comment on the nature of the upper mantle beneath Kutch as deduced from the xenoliths, and characterize the probable nature of source for the alkaline rocks, which generally occur, as I said, in the form of plugs, dikes, or even in the form of flows. Normally it is very rare sort of a occurrence, an alkaline magmatic rock, generally or magma, producing lava flows. There are very small scale, but they are seen present in this particular region as such. Okay. So you are quite familiar with this particular diagram as such, which gives you the distribution of the Deccan volcanic province as such, and in that to a great extent you can see two colors, one is green and the other one is blue, basically speaks about the classification that we normally follow in case of Deccan volcanic province, that is the compound flows and simple flows, or Pa or A flows, similar to basically your Hawaiian tholioids as such. And then the tectonic element that if you look at, the Narmada zone lineament that occurs, or the rift that occurs to the north or just close to the Malwa plateau, and onto the west coast basically you have the west coast fault, and there is a Cambay basin or the Cambay rift, and that is considered to be a triple junction wherein three linear features are meeting at one common point as such. So generally, like in case of the East African system that we speak of, the East African, then the Afar plume and the other arm basically, wherein to a great extent two of them are failed arms and one is active as such. So that is what is a characteristic feature of a triple junction, and perhaps that is what people envisage, that probably the Cambay represent a triple junction where these three linear features meet at a common point as such. This is what the geological map given by Biswas long time back in 70s perhaps, and herein you can see the distribution, various different rock types. Basically the Kutch region is known for the occurrence of Jurassic rocks, and within which basically you have these Cretaceous, and even the tertiary sediments are also seen present as such. Okay, and generally you get to see in the central part, this particular one, this is what is called as a median high. So there is a uplifted portion in the middle, and these are the distribution of basically various fault, the Kathiawar fault, and this is the Alaband fault basically. The basement is not exposed anywhere in the close proximity of this particular region as such. So, and it is believed to be basically a failed rift system and allocogen as such. And these are basically the various different rock types. There is a classification been given as such: the Catrol series, the Habbo series, the Bhuj series. And Deccan troughs, and then you have tertiary sediments as well as quaternary. So the Catrol, Habbo, Bhuj, up to Bhuj, perhaps Bhuj is the beginning of the Cretaceous part. In fact, there is a marine as well as fluvial, and the Bhuj to a great extent basically are transitional rock type. They show both at the lower part marine and then is more of a fluvial environment as such. So those are mostly sandstones. And then you can see there are number of dots that you can see: Jura, Jumara, then Kira, Chari, Habbo. These are all basically are called as dome structures. So there is a ultramafic or mafic material which has uplifted the portion there. So in the central core part, normally there are magmatic rocks being seen present, but rest of the sedimentary envelope is seen uplifted, giving more like a circus tent like structure as such. So all the dips are in a radial fashion, basically moving away from each other. So those are to a great extent are the domal structures been seen reported over here. And apart from that, there are many other regions where there is a alkaline magmatic rocks commonly been seen present, mostly in the form of plugs, sheet-like bodies, or sometimes as even as dikes also. Okay. So this is what is the stratigraphy. The previous classification is the older classification following the code of stratigraphic nomenclature. This is the recent classification again given by Bishwas: Jureo formation, Jumara formation, Juran formation. All these are Jurassic in age, and based on the basically fossil assemblage, they have been classified into basically Upper Bathonian to Calovian, Jureo formation, Calovian to Oxfordian, the Jumara formation, Argovian to Neocomian, the Jumara formation, Juran formation, and on top Neocomian to Santonian, basically more or less the lower Cretaceous part as such, that is the Bhuj formation. And then you had the Deccan traps, Upper Cretaceous to Paleocene, which to an extent have flows with intertrapping beds as well as intrusive dikes and plugs. Okay. I will not get into the details of every formation. This is the Booger gravity map, basically to an extent tells you about which are the areas where there is a magmatic underplating, magma has come to a shallower depth. Those are basically showing higher Booger gravity anomalies as such, and for that purpose basically when you overlap the geological map on this, you generally find most of these areas are setting down below the plugs or to a great extent the domed up areas as such. Okay. So just to gain a further confidence through geophysical means, this is the study area, and as in the beginning only as I mentioned, this study was done by Raymond Durai Swami, and the geological map also he himself has prepared this, and these are the locations you can see. In fact, the red one, those are the alkaline plugs. So there are more than about 50, the larger one to a great extent are shown plotted over here, and there are many dikes also, you can see them. So these are dikes and sills, like for example Paya or at Hawaii or near Sumrasar. So these are basically the red one are the alkaline plugs or sheet like bodies, and these are the dikes. This is what is the general distribution commonly been seen. And then to the south, all this green patch that you are looking at are generally the Deccan basalts. Okay. So to the north of that, most of the distribution of the alkaline plugs is seen. Okay. So these are some of the pictures of the alkaline plugs and the beautiful columnar jointing, very delicate one been seen preserved in some places as such. This is a Withon area basically. In fact, you can see a sort of a valley in between, and that to an extent is more of a faulted impression of a fault out there. Then this one to an extent is the Withon plug. This is basically the Dinodar Dongar. So different localities with different sizes of plugs and sheet-like bodies, which to an extent entrain the ultramafic zonales of a very small size that we already have spoken about and looked at day before yesterday. This is the Dhruvia hill. In fact, On this particular region, there is a mining that goes on basically over here, and this is the actually the neck part, you can call it to be, where there is a concentration of more amount of xenoliths over there, okay, of larger size in this particular year. But larger in the sense, when you try comparing it with the previous picture shown by Michel, compared to that they are very tiny, 1 to 2 centimeter, 2.5 centimeter, and that basically was the problem. Although they are present, but how to calculate and how to work the chemistry, and that's how basically this whole thing was taken to Australia, so as to understand the mineral chemistry and various different aspects of it as such. So these are the alkaline lava flow that you can get to see. In fact, the characteristic sort of a red bowl that is seen separating, and this is the alkaline lava flow that has been seen present over here, a very rare kind of a, because normally the alkaline magmatic rocks occur in the form of plugged sheet-like bodies, very rarely as a individual lava flow as such. Okay. This we already have seen how the xenoliths are disposed, what is their size. I am going to rush through these because I don't want to repeat them. These thin sections we also already have gone through, and the last time I was mentioning about basically the morphology of spinel to a great extent, and you can see they are different shapes and forms, and they are to a great extent are indicators of the stress regime. So you to an extent can understand on the basis of this morphology, for example, the leaf-like structure, or sometime as you can get to see even kind of a zoning over here. Then outside the domain of orthopyroxene, this is what basically sometimes they are seen included as inclusions or as exclusions within the pyroxene, and with basically this thing they come out of the main domain and then start growing, and during this growth basically they display variety of forms or shapes as such, and those been used as basically indicators of the stress conditions. There's a special work been done by a group of French scientists led by Nicolas, and based on which to a great extent they have defined certain structures or textures, the protogranular or porphyroclastic and so on and so forth. Many of them are, this we already have seen, these are occurring as exsolutions, and these are rutile exsolutions indicating mantle metasomatism. The secular variation basically with respect to the Mg number and the modal olivine content, this is what the train normally you get to see for the phanerozoic larzolites, and most of these xenoliths basically are, few of them they follow this trend and few are they are away from this thing, but they are definitely outside basically this particular domain, the Archean larzolite and Harzburgite, which Michel spoke about from the Kappaul Craton or the other regions as such, whereas over here they are mostly coming from basically younger phanerozoic part as such. Okay. So they relatively represent a younger subcontinental lithospheric mantle as such. So olivine Mg versus modal olivine, the relation between melt depletion and residual peridotite composition. Few samples follow the oceanic trend of void. Such deviation from the oceanic trend is similar to the cratonic peridotites, but they are definitely not cratonic peridotites. Positive correlation between modal orthopyroxene Ni from the olivine similar to the observed by Boyd. Such a positive correlation may reflect SiO2 enrichment of a high Mg protolith by reaction with small degree of silicic melts from subducted eclogites with overlying peridotite. These are various different speculations. What is the correct one that we'll be looking at? Correlation between Mg of olivine and clinopyroxene, orthopyroxene from the spinel larzolite generally from Kutch. The triangular, the tighter correlation between Mg of olivine and orthopyroxene, indicating greater chemical equilibrium between the two phases. So this is for olivine, the various different trace element Ti versus basically Cr, Ca, then Mg number versus the Ni. Those are to a great extent indicate about how much amount of differentiation or fractionation these magmas have undergone. So the tight correlation basically suggests they are more primary magmas, and how primary are they, whether they can be considered as the liquid which are not differentiated. When you basically the pyroxene compositions, if you plot them, you can get to see them getting plotted into the enstatite region over here and diopside. So this is what is basically the chrome diopside and enstatite, which is to a great extent Al rich. So in this pyroxene tetrahedra, basically the classification has been done. So diopside and enstatite, these are the two pyroxene phase that you have. The OPX, again, individual minerals and their chemistry has been actually tested. What kind of correlation do they show? Mg versus Al2O3, Ti versus Mg number, then Al2 versus Al2O3 of the spinel and Al2O3 content of the orthopyroxene, because in most of the cases they are seen present as inclusions or as exsolution features within the orthopyroxene. So both are aluminar rich as such. So whether they have a cogenetic origin or one is getting exhaled from the other, and what is the process as such. So this is also again been tested for the CPX, the Al2O3 versus various different parameters been plotted, and you get to see either positive negative correlation that speaks about the melting conditions and the differentiation process the magma has undergone as such. This is what basically the data for the chrome dioxide, and in fact you can see the xenolith which shows a population from 4 different regions. This is from one locality called as Dinodar Dongar. This is the Saila Devi. This is basically coming from the Dhruvia, and this is coming from Bhujia. So the xenoliths which show a distinctly different sort of a trace element geochemistry as such. For example, over here you can see many of them showing basically the trend should have been this way, as Michel was talking about, when they are products of partial melting, but instead the lighter rare earth elements shows enrichment. So that is an indication of a metasomatism, more of a metasomatism, which has caused this particular enrichment. But again, the enrichment is not similar everywhere. Okay. So here you can see, in fact, here it is going almost to 100 times than the primitive mantle, whereas it is over here only 10 times than the primitive mantle. And here, in fact, you can see some spikes are there. Probably it's not a very correct data as such, but rest all you can see. Generally, few of them are very depleted with respect to titanium, zirconium, and so on and so forth. But the characteristically, all of them to a great extent show a positive niobium positive niobium anomaly as such. So these are based on the trace element characters. With to an extent we did the trace element modeling following the work done by Norman in 1998, and wherein both batch melting and fractional melting, both the conditions were tested, and the basically for which whatever elemental concentration that has been seen present in the clinopyroxene, that has been made use of. And these are basically the various different basically I would say CCPX is the constant. This is by basically the equation that has been followed, and which to an extent this denotes what are the parameters that are involved as such. And following that, you can see, in fact, there is a curves that are established as such. You can see a few of the elements, for example, over here, the yttrium versus ytterbium, all they follow this melting curve as such, both for batch melting and as well as for fractional melting as such, and whatever range, whatever basically the mode of melting, but generally the maximum melting that has been recorded is only up to 15% as such. But at the same time, when the same sort of a trace element modeling is done for the taking other elements into consideration, for example, ytterbium versus neodymium, you can see a big spread does not follow basically this melting curve. Here you can see this follows a melting curve, but actually the distribution coefficient was changed considerably, and therefore it follows over here. Here also the same Ti upon Tn, and here you can see a big spread. It's not following this model curve basically, indicating something, some other process have operated upon, and which is the likely process. It is the metasomatic process that has caused the change in the concentration level of various other elements as such, whereas the Ya and the yttrium and ytterbium has not been modified, has remained the same as such. The rest all of the elements show a big spread, indicating their concentration levels have increased, and the increase in the concentration level is not due to the partial melting process. They do not follow the partial melting curves, but instead basically there is some other process probably may have operated upon, and that likely process is possibly is the metasomatic process. And yesterday he spoke about the 3 different kinds of metasomatic activity or metasomatic classification that he gave it to you: modal, cryptic, and the third one basically. Here it is more of cryptic kind of a metasomatism. So generally there is a change in the chemistry, but not change in the mineralogy. The minerals have remained the same as such. Okay. And then basically just to test the nature of the spinel, they are typically of ultramafic xenoliths, not of podiform type or stratiform type, which are the chromium xenoliths normally that we get to see. So they are not to great extent or cognate or related to any igneous process, but instead they are part and parcel of the ultramafic mantle that exists as such. Okay. So this is what we already have seen this particular diagram. Generally, just to test how much amount of partial melting, and with increasing degree of partial melting, you can get to see the CR number goes on increasing as such. And here to a great extent, when you plot CR spinel of CR number of the spinel versus the Mg of the spinel, again you can get to see this is what is the trend, and they follow again over here 1 to 9% of partial melting. So whether it is a batch melting or whether it is fractional melting, the melting basically doesn't exceed more than 15%. So limited amount of partial melting. So they are product of basically limited amount of partial melting with superimposed sort of a enrichment process of metasomatic activity as such. So that is the combination that seems to have played an important role in modifying the composition of the subcontinental lithospheric mantle as such over here. And these are the temperatures those been obtained as such, making use of various different geothermometers, and you can in fact get to see the temperature is also limited 884, 870 or 908, 903. So in the range of 850 to 900 degrees centigrade, again indicating basically they are coming from very shallow depth. So they are not of deeper origin, but they are belonging to spinel stability field perhaps. Of course, there was no indication, there were no index mineral to find out the pressure content as such, but basically the temperature and superimposing it on the previous established geotherms, it generally shows that they are coming from a depth range of 40 to 45 kilometers as such. So they are coming from much very shallow depth. When we look at the plugs as such, generally as I said, variety of alkaline igneous rocks, which include basonite, melanephelinite, nephelinite, alkali olivine basalt, and there are rocks such as very lamproite looking and compositionally very similar to lamproite. Over here you can see in fact one of the plug, these are the olivines and the phlogopites are there, and rest all basically the other varieties, basonite, melanephelinite and so on and so forth. So a subtle difference between basonite and melanephelinite. When there is appearance of plagioclase feldspar, we call it as a basonite, and when it is absent and nepheline dominated both in the mode as well as in the CIPW normative mineralogy, we call it as a nepheline. The ways and means basically to classify these rocks. Okay. And these are to a great extent the alkali olivine basalt. You can see basically many of them, these are the olivines. These are the typical tholeitic rocks belonging to the Deccan tholeitic province as such, and they show a variety of texture. This is a typical porphyritic texture as such. Then many times the olivines are seen to have been resorbed, so the magma seems to have reacted with it. This is what basically embed nature of many of the pyroxenes or olivine that is being seen. So there is an interaction between the basically the early form phenocryst and the late form magmas as such. And when you make use of the chemistry, making use of the task diagram, the Na2O versus plus K2 upon the SiO2 content, for classification of these fine-grained volcanic rocks, you generally find them to be varying between tephrite basanite to foidite, okay, many of them. And these are typical basically the subalkaline basalt belonging to the Deccan volcanic province as such. So you have two different types of magmas present in the same area. One are tholeitic in character, the other one are more or less alkaline in character, and they are mostly follow this particular classification, tephrite basanite or foidite. And for while doing the classification further on the basis of the normative nepheline content, you can see in fact this is what basically the basanite and melanephelinite distribution has been seen. So some of them are very transitional, they neither completely are basanite or melanephelinite, somewhere on the border, but few of them completely defined two different fields as such. Okay. The major oxide variations, basically again the Mg number, so as to find out how differentiated is the magma, because Mg number is a differentiation index, and with respect to basically the partial melting, what changes have occurred with basically the partial melting in the given element. This is the major oxide content P2O5, L2O3, CO and SiO versus the Mg number. So basically a positive or negative kind of a correlation that again speaks about how basically the evolution of the magma has occurred as such. Okay. And again making use of the same chemistry, to an extent you can find out the tectonic setting as such, and you can see although they are present in the continental domain, but most of them actually when they are plotted in this diagram are belonging to the ocean island basalt, the OIBs. Compositionally they are very similar to the ocean island basaltic magmas, which to an extent again we have seen during the lecture that they are product of small or large hotspots or mantle plumes as such. So to a great extent the hypothesis that we had thought of, that the alkaline magmatic activity and the tholeitic flood basaltic magmatism is something very similar to basically the Hawaiian type magmatic activity, to a great extent you find a support coming from even the chemistry. In all these diagrams you can see them basically getting plotted into this particular field, that the OIB, ocean island basaltic magmatism. So they are very similar to, compositionally similar to the OIBs or ocean island basaltic rocks as such. And this is what basically the chemistry, when the multi primitive mantle values are taken from Huffman and they are normalized, all the trace element data have been normalized, you can see in fact here also instead of there is a rising sort of a trend as such. Okay. So they have been derived from basically a mantle which to an extent seems to have been the enriched mantle as such, and therefore all these I would say the light rare elements shows enrichment as such, rest all are basically showing the various different anomaly that you get to see. The negative PB anomaly indicates basically they are not assimilated or crustally contaminated magmas, so they are more or less primary in character. And then this particular enrichment pattern also speaks of more or less basically they are coming from an enriched source. When we speak about the mantle, the depleted or enriched or fertile and sterile mantle, that is what normally we speak of. So and more of an enriched mantle perhaps was involved in the formation of these particular rock types. Now in most of the cases basically these what are called as the HRE, heavy earth elements, which to an extent are not very fractionated, indicating they are not coming from the garnet stability field, but they are coming from spinel stability field. So although the magma must have been originated relatively at a deeper level from the xenolith basically, but same time again they are not very sourcing a deeper mantle. They are still in the realm of basically your spinel stability field or spinel mantle as such. So the depth of magma formation is not very deep as such. Okay. When you look at basically the alkaline rocks, basanites and alkali olivine basalt, they again show, the previous were melanophyllite, the basanite and alkali olivine basalt, again they more or less show a rising pattern enriched with respect to basically the light rare earth elements, again indicating more or less an enriched sort of a source, involvement of an enriched source in the generation of these magma gases. And when you look at the tholiids to a great extent, they can be further divided into low Ti basalts and high Ti basalt. The titanium content, again speaking about the relatively shallow depth and deeper depth for the magma generation, even in case of the tholiid series as such. So generally when you compare them with the alkaline rocks, here you can see the low Ti basalt more or less show a relatively flat pattern. There is not a significant enrichment. There is an enrichment with respect to the primitive mantle values, but not very significant one as such. For comparison, in fact, you can see this is the MORB data for comparison purpose as such. So with respect to the MORB, they are showing relatively higher enrichment as such, but again still then to a great extent they are not showing a negative PV anomaly. So there is again, even the tholitic basalts also are more differentiated but not contaminated one. Okay. So they have undergone fractionation and differentiation in the magma chamber, but there is no significant sort of assimilation with the crustal material as such. So xenoliths are considered to be windows to the mantle processes. You have depleted and fertile xenoliths, partial melting basically low, less than 5% partial melting, and higher, greater than 10 but up to 15%. The temperature that you get to see is low equilibrium temperature, indicating basically they are coming from shallow depth and not very deeper levels as such. So the overall depth is worked out to be more or less 40 to 45 kilometers, and there is evidence of cryptic modal metasomatism. That is what we understood on the basis of the trace element modeling as such. And this is what is the geotherm that was established basically for the Murud-Janjira region, the west coast region. We have superimposed our data on this geotherm, and you can see in fact this spinel lazulite from Kutch, that is present study, they get plotted in this particular region. So this is the depth 40 to 50 kilometers, that is the depth range basically they are all getting plotted to, as compared to basically the west coast geotherm, which to an extent a very elevated one, and here you can see they are coming from a relatively more shallow depth in the range of 30 to 10 kilometers as such. So, and that is what I believe that basically the Madagascar and Sayadi Mala, which to an extent were part of the western continental margin, during basically the opening of the Indian Ocean, that is at 60 million years before time, due to the plume interaction, there is a breaking of, there is basically breaking of the western continental margin, which has moved away. Okay, the present I would say the Sayadi Mala or Seychelles Islands, they got broken away, and during this particular extension process, obviously the western margin has been thinned considerably. So the mantle to crust to mantle, that is the moho, is present at very shallow depth in the western region as compared to the Kutch region, which is relatively present at deeper levels. This is what one can deduce on the basis of this particular geochemistry or this particular basically temperature pressure diagram, which is a geotherm as such. So the in fact the west coast region, you have variety of xenoliths, mostly pyroxenite, granulites and spinel larzolite, whereas Kutch you have uniformly one single sort of a crop. Most of them are basically the spinel larzolites, and they are all getting plotted in this particular region. Basically you can see, in fact, this is this field for the spinel larzolite, and you to an extent can work out. So they are coming from say around 45 to as deep as 50 kilometers. That is the maximum depth from where the xenoliths are recovered as such. Okay. So the estimated pressures are obtained on the basis of the absence of both plagioclase and garnet in the xenoliths, and by referring the temperature to the west coast geotherm, which is roughly around 15 kilobar, 40 to 45 kilometer depth is the basically the depth of the origin for the xenoliths. The minimum heat flow of 60 to 70 milliwatt per meter square has been computed for the Kutch xenoliths, which is closely comparable to the oceanic geotherm. Okay. So more or less a shallow kind of an partial melting activity at a shallow depth as such. Okay. Then when the trace element data is compared with the ZR versus Y upon NBA versus Y of the Kutch xenoliths, the Kutch xenolith, and this is basically your alkali basaltic magmatic rocks as such, you generally find that there is to a great extent a array between these two end members as such. So probably during the emplacement, the magma has picked up some characters of the subcontinental lithospheric mantle. So in fact it had a time to equilibrate or to at least make some exchanges with the subcontinental lithospheric mantle, mimicking some of the characters of the subcontinental lithospheric mantle. So although it is not completely assimilated or fractionated, but it did have certain reaction or certain interchange or exchange of element basically with the subcontinental lithospheric mantle. So just to find out how much amount of partial melting so as to produce this alkaline igneous rock, generally alkaline magmatism is produced by very small scale magmatic activity, small amount of partial melting in the range of about say 1 to 5%, not more than that. And here you can see, in fact, when all the data has been plotted over here, the low TI basalts basically are in the range of say around 0.5 to 2% of partial melting, whereas the high TI basalt is into this particular range. So the continuous lines are non-model fractional melting curves calculated for 4 mantle composition, that is basically your spinel peridotite, then spinel dunite, garnet peridotites and garnet bearing dunites as such. And in that most of your data plots between basically in a shallow depth. Okay. So and the amount of partial melting is very limited as such. You can see, in fact, 2 to maximum of around 8% of partial melting, whereas in case of the high TI and low TI basalt, it goes down further when you plot this particular data La upon YB versus TB upon YB, and then the subalkaline basalt show a relatively smaller amount of partial melting as compared to the basonite and foidite and other things. Okay. So the host alkaline rocks are characterized by strong but variable enrichment in incompatible trace element, indicating derivation from a trace element enriched mantle source. Trace element signatures identify an OIB type source as the dominant component for the silica poor mafic alkaline rocks, and an additional component derived from the subcontinental lithospheric mantle SCLM as represented by the spinel larzolite xenoliths. So between these two end members, the magma has moved and been evolved as such. Subcontinental lithospheric mantle component has geochemical characteristics that overlap those observed in spinel larzolite xenoliths entrained in these rocks. Phlogopite and apatite in the SCLM are of metasomatic origin attributed to the infiltrating fluids and or melt derived from rising mantle plume material.
The composition of the alkaline rock is consistent with a regional upwelling of deep mantle related to marginal rifting and with OIB type geochemical characteristics. Thermal inhomogeneities within such plume swath resulted in small dye piece which may have undergone melt segregation at the base of the lithosphere and incorporated varying amounts of SCLM during its ascent. So this is what the deductions that we have made or inferences that we have drawn. The mere presence of mantle zoology in these rocks does not necessarily mean that these erupted lava represent direct mantle or primary melt, but have undergone little crystal fractionation en route to the surface. Common phenocrysts like olivine and clinopyroxene, nephelinite and basanite are invariably complexly zoned. So it is not relatively very primary and primitive magma which has not undergone any differentiation. It did go a certain amount of fractionation, and that is being shown in the textures that are displayed, or the chemistry or the zoning the individual minerals basically they show. Comparison of the bulk rock measurement chemistry of these silica poor mafic alkaline rocks with experimentally determined high pressure will indicate that the Kutch rocks mainly represent partial melting of a carbonated mantle lazurite followed by olivine and clinopyroxene controlled fractionation and magma mixing as exemplified by complex and reverse zoning of phenocrystic phase. Thank you. So in most of the time basically in our regular classes I go on speaking about the alkaline magmatic rocks from Kutch. So this is the actually a complete sort of a review of what we had done over there. Okay. Any questions, any queries?